Hi, welcome back to Reading Research Paper series. Today we are looking at Swin Transformer paper. It's a very nice Saturday morning. I'm sitting down to record this at 7:30 a.m. right now. I feel so good and so fresh. So I have gone through this paper maybe 3 times now. And I must say that although this is an excellent idea, the paper is incredibly good. The idea is fascinating. I personally don't think the paper is really well written. Of course, it's well written from a point of view of let's say somebody who already knows in and out of Swin Transformer. But for someone who has not thought of this idea before, you will struggle with it because it's so dense. The authors have been very, frugal with respect to use of words, especially in some sections where we will discuss shifted window. Although the idea on a broader level is easy to understand, the exact implementation is a little bit complex, and the way the paper is written was honestly to me a bit frustrating. But the good thing is I have already spent a lot of time understanding the nuts and bolts of this paper. I have also made some diagrams which are different versions of the figures in the paper themselves, which I strongly believe will help you better probably as a beginner. And when I was reading the paper, I initially read it myself, then used ChatGPT to get some explanation of some areas where I struggled. And then also I was failing. And then what I did was some concepts I decided to visualize myself. So I opened Figma and then I created some visualizations of shifted window, etc. We'll come to all of that. I'm just saying my experience first. And once I did that, things started becoming more clear. So from that point of view, I'm very proud of the way I have approached this paper, because it was conceptually difficult, although it's a short paper. So I have the printed copy of the paper with me here, and it's only 14 pages or something. And even in that, around last 4 pages are references. So the paper is not a long paper. The second half of the paper is a lot of tables with results where the classification, object detection, segmentation, etc. is compared with the state of the art. So there is not much intellectually challenging in those pages. But despite all of that, I found the paper very technically dense. And in my opinion, it's not because the idea is difficult to understand, it's more because of the way it's written. Maybe someone else feels differently, but this is how I felt when I went through the paper multiple times. Now, in this series, we have discussed about Vision Transformer, data efficient image transformer. So it's like a very nice transition to Swin Transformer because it is an extension of what Vision Transformer could do. So of course, you should understand how Vision Transformer works. A little bit we'll discuss today, but if you don't know anything about Vision Transformer, I recommend you to go through some 10-minute YouTube video from any channel. That will be a good start. But as always, we will pick up the paper on Miro board. I have constructed the annotated Miro document, and we will go through the paper line by line. We'll try not to skip anything. Whenever there is a question that we have, we will ask that to ChatGPT in the hope of explaining certain things in a easier language. For some figures, I have constructed my own versions in the hope that it can explain things better to you. So we will go through all of that. And then lastly, we'll spend most time on the architecture, of course. We want to understand what is the Swin Transformer architecture, but we'll also go through the rest of the things like results and what are the different types of experiments the authors did, and what are the different ablation studies they conducted. This paper came from Microsoft, and it has specifically Microsoft Research Asia, and it has almost 38,000 plus citations. So it's a very, very well-known paper. In fact, it's a seminal paper. Although I don't like the way it's written, the idea that they introduced, I would say it's really a pivotal one, because they showed that you can construct CNN-like hierarchical features using, just by using transformers. So there is no convolution operation. It's just transformer. But there, they use the idea of windows and shifted windows. So that helps you first construct an attention which is not necessarily global. So that's the number one thing. So their vision transformer they introduced in this paper is much faster. It scales linearly with respect to the image size, unlike vision transformer whose attention complexity scales quadratically with the image size. When I say image size, I simply mean the number of pixels. I know that you are not fully understanding what I'm saying. I'm just spending initial few minutes to just discuss why this paper is significant so that you have enough motivation to go through the paper. And they showed that maybe this paper can become like a backbone architecture where transformer is the key component. None of the papers before this probably could make that claim, and Swin Transformer I think can make claim. So the sentence or the wording that they use is, this paper presents a new vision transformer called Swin Transformer that capably serves as a general purpose backbone for computer vision. We know that the backbone typically for computer vision is CNNs, different CNNs. But here they are showing, in my opinion, probably for the first time, that you can use a relatively efficient and state-of-the-art transformer architecture as a general purpose backbone for computer vision tasks. We know that transformer is a general purpose thing for NLP, but not for CV. But here they are showing it can be the case for CV also. So that's most of it. I'm hoping that this lecture or this video I can record in one sitting. If not, maybe I'll take 1 or 2 breaks. I'm not sure. I can only while recording, but I feel pretty good and energetic right now. But I'm also expecting to be very tired by the end of going through this paper. You may also experience the same thing. It's not you will definitely experience the same thing. So feel free to take enough number of breaks. Feel free to take it slow. There is no rush. You can take as much time as you want to go through the papers, but just make sure that you're going through it fully. I recommend you printing it like this. It's only 14 pages. Have a printed version next to you as you are going through this video, and then just annotate or underline or have a notebook next to you so that you can write down a few points. So it's your engagement, your involvement with this paper is a bit more interactive and engaging rather than just passive. Passively reading is in my opinion, is not the best thing to do. All right, I think that's most of the things which I wanted to mention as an introduction to this paper. A great idea, but not the easiest papers to understand. So let's see how we can kind of dissect this paper and try to understand it in the best possible way. So let's now start looking at the paper. This is the Miro annotated pages of the paper. I don't think this will take too much time except for the section about shifted windows and its implementation. There is also one part where we will have to spend a little bit of time, which is relative positional bias. I'm just mentioning these terms so that when you reach that point, you are not surprised, you know what to expect. All right, so the paper, if you can just Google Swin Transformer paper, it will come up and you can see that 38,000 plus citations. You have the copy available on archive. And this is the full paper. It has 14 pages as I mentioned, and last 4 pages are just references. So in effect, it's like a 10-page paper, 2 columns. So the number of words are, I would say, per page is quite high compared to data efficient image transformer paper, and because of that this will probably take more time for you to go through. But I mean, that's part of the fun of reading research papers, right? Fun meaning just like going to a gym, like you are working out intellectually and you will be tired at the end of it, but you will come out with a feeling of high amount of reward. So the paper title is Swin Transformer Hierarchical Vision Transformer using shifted windows. So the name Swin came from shifted S and windows. When I looked at some YouTube lectures based on Swin, people were, this is from Microsoft, so people were commenting about the Windows operating system. There were some jokes which I forgot what it was, but people were mentioning something about the Windows OS itself in this context. But anyways, that's the title of the paper. It's from Microsoft Asia, and let's get into the abstract. This paper presents a new vision transformer called Swin Transformer that capably serves as a general purpose backbone for computer vision. Challenges in adapting transformer from language to vision arise from differences between 2 domains, such as large variations in the scale of visual entities and high resolution of pixels in images compared to words in text. So this was an interesting thing, right? Why do they say that the pixels are of higher resolution compared to pixels in an image can be of higher resolution in an image compared to words in a text? So the main thing is that if you have a set of words, or to represent a certain idea, the idea of a cat jumping over a fence or something like that, if you want to represent that idea, you have to use certain number of words, right? So if you have n number of words, it can only represent so much information. And in images, to represent same idea, if it's an image of a cat, the basic element of the image, unlike word in text, which already carries a meaning, the basic element of an image is a pixel. You can have an image of a cat that is ultra high resolution. It still represents the idea of the cat, right? Or you can have a low resolution, highly pixelated image of a cat. At the end of the day, both refers to cat. So here I have borrowed a sentence which I got from ChatGPT. I thought it was a very nicely written sentence. That's the reason why I'm exactly putting it here. I just want to read through this. In NLP, a single token represents either a whole word or subword, right? And this token already contains a fairly meaningful piece of information at a much higher abstraction level. So you can say that text tokens are low resolution signals because you do not worry about tiny details inside that token. So just read the sentence. Text tokens are low resolution signals because you do not worry about tiny details inside that token. In images, however, you treat each pixel as an individual token, or I'm not saying you should treat, I'm saying if you treat each pixel as an individual token in the image, just like how you may treat one word as an individual token in the text, then you are operating at a very fine microscopic level with enormous resolution. You are zooming into an image a lot. If you are only looking at one pixel, you will basically see nothing. That image will not, you're overly zoomed in to make any meaningful sense, but it's because image has a much higher resolution. But if you are zooming into a book and into a page, into a paragraph, and then into a sentence, and then into a word, by the time you reach that zoomed in level, the token, which is like a word or subword, is already having a lot of information. But if you do the same level of zooming in, look at the image, look at some section of the image, and then zoom in further and look at a pixel, you don't get that kind of meaning. Which means there are many hundreds of thousands of tokens inside even a medium-sized image. And most of them do not carry meaningful semantic information by themselves because a pixel does not have any independent meaning without its neighborhood context. So a pixel as an independent entity carries no meaning. A word or subword as a token can carry a lot of meaning. So there is a huge difference between natural language processing and computer vision, simply because of how you may think about one token. To address these differences, we propose a hierarchical transformer whose representation is computed with shifted windows. So what do they mean by whose representation? Representation meaning the transformer is using shifted windows to create representations of images. The shifted windowing scheme brings greater efficiency by limiting self-attention computation to non-overlapping local windows while also allowing for cross-window connection. So in the Swin transformer, you will see that there are two transformer blocks. One is window-based multi-head self-attention. Second is shifted window-based multi-head self-attention. In window-based self-attention, you are preventing the self-attention or you are constraining it to just inside one window. You can think of it as, let's say the image is 10 by 10 patches. Each patch, you know what is a patch from Vision Transformer. Patch is like a collection of pixels. You divide an image into a bunch of patches. And let's say each window is consisting of 4 by 4 patches. Then you are constructing the attention just between those 4 by 4 patches. So 4 by 4 means 16 patches. So 16 tokens paying attention to themselves. Rest of the patches are not considered, right? So it's called local attention. So that is one thing which Swin Transformer does. But another thing is, because not having global attention is an issue, because the whole point of using transformer is so that it can attend one token in one corner of the image can attend to another token in another corner of the image. So you can have long range dependency. That's the whole reason why transformer is being used. So how do you do that? For that you introduce the shifted window idea. So why is this beneficial over vision transformer? The reason why this is beneficial is because when you are paying a global attention, if your image size is 100 by 100, then or when I say 100 by 100, I mean number of patches. Let's say there are 100 by 100, that many patches in an image. Then you have basically 10,000 patches. So the complexity of your attention score calculation will be 10,000 multiplied by 10,000, because you have 10,000 queries attending to 10,000 keys. So we will discuss about this in detail once we reach that section in the paper, but I just wanted to give you a brief idea. So just understand why Swin Transformer was important. This hierarchical architecture has the flexibility to model at various scales. We'll see what this various scale means. A representation is shown in this image, but we'll come to this. And has linear computational complexity. This is very, very important. Please pay attention to this. Swin Transformer has linear computational complexity with respect to image size, and Vision Transformer has quadratic image complexity with respect to image size. These qualities of Swin Transformer make it compatible with a broad range of vision tasks, including image classification, and they got 87.3% top 1 accuracy on ImageNet 1K, and dense prediction tasks such as object detection, so 58.7% average precision, 51.1% on COCO test and dev dataset, and semantic segmentation accuracy, 53.5 mean IOU score on AD20K validation set. Basically, they are performing really well. The Swin Transformer performs really well on classification, detection, and segmentation. Its performance surpasses the previous state of the art by a large margin of plus 2.7 box average precision and plus 2.6 mask average precision on COCO dataset and plus 3.2 mean IOU on AD20K, demonstrating the potential of transformer-based models as vision backbones. So this is one big claim the paper is making, like you can use transformer based architecture as a vision backbone instead of CNN, and here is the proof. That's what the paper is claiming. The hierarchical design and shifted window approach also prove beneficial for all MLP multi-layer perceptron architectures. The code and models are publicly available on this GitHub. We can actually open the GitHub. I'm just curious to see how many stars this repo has. Swin Transformer GitHub. It has 15.4k stars, so very famous GitHub repository. Okay, so that is the abstract. Let's move to the introduction. Modeling in computer vision has been long dominated by CNNs. And its revolutionary performance on the ImageNet, beginning with the AlexNet model and its revolutionary performance on the ImageNet image classification challenge, CNN architectures have evolved to become increasingly powerful. We know that. Increasingly powerful through greater scale, more extensive connections, and more sophisticated forms of convolution. With CNNs serving as backbone networks for a variety of vision tasks, these architectural advances have led to performance improvements that have broadly lifted the entire field. Basically, architectural improvements in CNN has broadly lifted the whole field of computer vision itself, because CNN based models have become the backbone architecture in any computer vision task. On the other hand, the evolution of network architectures in natural language processing has taken a different path, where the prevalent architecture today is instead the transformer. So in NLP, it's not obviously CNN, it's a transformer based architecture. Designed for sequence modeling and transduction tasks, the transformer is notable for its use of attention to model long-range dependencies in the data. So that's the main thing. The main reason why we use transformer is because it doesn't matter if two tokens at the two extremes of the sentences, if they are highly related to each other. So consider the sentence, the teacher who was teaching a difficult concept to the students smiled. So the word teacher, which is at the beginning of the sentence, and the word smiled at the end of the sentence, they are the most highly correlated. Although the students and the smiled word, they are close to each other at the end of the sentence, they are not related to each other, because students are not the people who smiled. Teacher is the one who smiled, right? So this is called long range dependency. And to capture this long range dependency, you have to construct attention scores or attention weights between queries and keys, which are the tokens themselves in self-attention. This is the reason why transformer became so useful in NLP, because within a sentence, the words can have long range dependency. Its tremendous success in language domain has led researchers to investigate its adaptation to computer vision, where it has recently demonstrated promising results on certain tasks, specifically classification and joint vision language modeling. I just want to check whether this 20th and 47th paper, I don't know which papers are they. Maybe it's Vision Transformer and one other. So 20th is, yes, Vision Transformer. This is the Vision Transformer paper. Image is worth 16 by 16 words. This is Alec Radford learning transferable vision models from natural language supervision. Okay, this is the clip paper. Yeah. This is the contrastive learning based, image pre-training. So the paper, what they were trying to do was, there were images and there were captions, and you wanted a model, like a vision language model, to learn how to represent, let's say, image of an apple and text that writes apple in the same way, in the same vector space. So that is this paper. Of course, we want to review this paper at some point. It's very famous. The only thing is it's very long. It's a 48-page paper. If we want to fully go through it, it will definitely take a long time. Anyway, so those are the two papers that are being cited here. In this paper, we seek to expand the applicability of transformer such that it can serve as a general purpose backbone for computer vision, as it does for NLP and as CNNs do in vision. So transformer is already a backbone in NLP, but CNN is a backbone in vision. Here, what they're trying to see is, can transformers become the backbone for vision tasks also? We observe that significant challenges in transferring its high performance in the language domain to the visual domain can be explained by differences between two modalities. What do we mean by two modalities? Text and image. One of these differences involves scale. Unlike the word tokens that serve as basic elements of processing in language transformers, visual elements can vary substantially in scale, a problem that receives attention in tasks such as object detection. In existing transformer-based models, tokens are all of fixed scale. We know that tokens are words or subwords in most of the transformers, a property unsuitable for these vision applications. Another difference is the much higher resolution of pixels in images compared to words in passages of text. So if we zoom in on the text and if we look at a word versus if we zoom in on an image and look at a pixel is even more zoomed in, basically, because pixel carries no meaning. It has no, it's too, you're zooming in too much when you are looking at a pixel level. So to consider pixels as tokens is impossible. Words or subwords still carry meaning. You can zoom in on a book, on a page, on a paragraph, into a sentence, into a word, into a subword. You will still retain some meaning. That's not the case with pixels. There exist many vision tasks such as semantic segmentation that require dense prediction at pixel level, because in semantic segmentation, we are classifying every single pixel in an image to class A, class B, class C, etc. So you need pixel level precision for semantic segmentation. And this would be intractable for transformer on high resolution images, as the computational complexity of self-attention is quadratic to image size. Why do we say that? Because let's say you have image of size height h and width w and patch size is p. Totally, how many patches do you have? N equal to, along the height you have these many patches, along the width you have these many patches. So total number of patches or total number of tokens is hw by p square. What is hw? Height, number of pixels along the height multiplied by number of pixels along the width, which is equal to total number of pixels in the image, correct? So this hw is the size of the image in terms of total number of pixels. Now, if you have n patches or n tokens, how many queries do you have? You have n queries. How many keys do you have? You have n keys. And you are taking dot product between every single query key pair So how many such dot products do you have? You have n times n, which is n square dot product. And what is n square? HW the whole square divided by p raised to 4. So you have to take these many dot products to construct attention scores. So the complexity of calculation of attention scales as the square of HW. And what is HW? Now, total number of pixels, which is the image size. So total, the attention complexity scales quadratically with the image size. That is what they have mentioned here. Complexity of its self-attention is quadratic to image size. To overcome these issues, we propose a general purpose transformer backbone called Swin Transformer, which constructs hierarchical feature maps. So please note this word, hierarchical feature maps, and has linear computational complexity with respect to image size. We'll come to how exactly it is linear. Let's not discuss it right now. Just understand that in normal transformer based architecture, the complexity of attention computation scales quadratically with respect to number of pixels. In Swin Transformer, it is linear. As illustrated in figure 1, Swin Transformer constructs a hierarchical representation by starting from small size patches and gradually merging neighboring patches in deeper transformer layers. So figure 1 we had just passed. This in page 1 was the figure 1. So this left hand side diagram corresponds to Swin Transformer's different layers. Right hand side is Vision Transformer. In Vision Transformer, we know that we are considering 16 by 16 patches usually. So if an image has 160 pixels, each patch you will have total 10 by 10. So totally 100 patches, right? Each patch will be 16 by 16. Like that, you have 10 patches along the row, 10 patches along the column, totally 100 patches. In Swin Transformer, on the other hand, the patch size changes with the layer. So I will show you the layers later when we come to the architecture part. But the reason why it's called as hierarchical feature map is because so here the patches are 4 by 4. Here it is 8 by 8. Here it is 16 by 16. Here on the other hand, all patches are 16 by 16. So in Vision Transformer, you are not looking at image from various different scales. In Swin Transformer, you are looking at the image from various scales. And these scales can be utilized separately for various different tasks. Just like how, for example, UNet works. I'm not sure if you know about UNet, but this is the architecture. In UNet also, they consider image at various resolution, feature map at a high resolution, a low resolution spatially, even lower resolution spatially, even lower resolution spatially, but number of channels are higher. I don't want to go into the details of this. If you are interested, I have created a UNet paper review lecture. You can search in our channel UNet architecture or something like that. You should get the link to that video. But anyways, let's come back to the paper. So figure 1, the proposed Swin Transformer builds hierarchical feature maps by merging image patches shown in gray. So here when they say gray, they simply mean this. I think they have added a gray color layer. It's not very clear, but yeah, whatever. Shown in gray in deeper layers and has linear computation complexity to input image size due to computation of self-attention only within each local window. So this red color thing is a local window. So let me zoom in. So this is a local window of 4 by 4 patches. This is also a local window of 4 by 4 patches. The only thing is patch size has increased. This is also a window of 4 by 4 patches, but now the patch size has increased. We have still not discussed how exactly is the complexity linear and not quadratic. That we will come to after a little bit. It can thus serve as a general purpose backbone for both image classification and dense recognition tasks. In contrast, previous Vision Transformers produce feature maps of single low resolution and have quadratic complexity to input image size due to computation of self-attention globally. So that's the main difference. Here the computation of self-attention is local in Swin Transformer. In Vision Transformer, it is global. It's global because for constructing the attention scores, you are considering every single image pixels that are part of every single patch. The whole image is considered just like that to construct the attention scores. In Swin Transformer, you only construct attention score first within this window separately, within this window separately. So you are not attending the patches in this window will not attend to patches in this window directly. The patches in this window will not attend to patches in this window. On the other hand, since there is only one, essentially there is only one window in Vision Transformer. All patches attend to all other patches. So that's the main difference, but we'll see why this is beneficial and all. I'm sure you have a lot of questions at this point, but we'll address all of that through the paper. With these hierarchical feature maps, the Swin Transformer can conveniently leverage, where did we left off? Yeah, we left off here. Conveniently leverage advanced techniques for dense prediction, such as feature pyramid network, FPN, or UNet. UNet I showed you. Feature pyramid network is also very similar. Feature pyramid network. Actually, there is a nice paper based on that, but let's not go into that. I'll just show you an image. So here, this feature pyramid network is like constructing, imagining the different features in different scales as like a pyramid. So small scale, medium scale, large scale. UNet also does something very similar. The linear computational complexity is achieved by computing self-attention locally within non-overlapping windows that partition an image. We will see why it is linear. We are yet to reach there. The number of patches in each window is fixed, and thus complexity becomes linear to image size. These merits make Swin Transformer suitable as a general purpose backbone for various vision tasks, in contrast to previous transformer-based architectures which produce feature map of a single resolution and have quadratic complexity. This is essentially what is shown in figure 1. A key design element of Swin Transformer is its shift of the window partition between consecutive self-attention layers. I'm sure you don't understand what this means because we are yet to look at the architecture. But in simple terms, the transformer architecture in Swin has two blocks. This is the, let's say, block number A, and this is block number B. So here you perform the window based attention score calculation. Here you do shifted window based attention score calculation. And then this whole block, this pair of blocks is called as the Swin Transformer attention block. And then this block itself repeats multiple times. I will show you the architecture diagram, so don't worry about this if you don't understand it fully yet. The shifted windows bridge the windows of the preceding layers, providing connections among them that significantly enhance modeling power. So basically, in the first transformer block, the windows are kind of not interacting with each other. In second shifted window also, the windows are not interacting with each other, but because shift is happening, some pixels that were in different windows in block number 1 will now be in the same window in block number 2. I will show that visually later, but just understand this much. In window 1, let's say you have pixel A and pixel B. In block number 1, you have pixel A and pixel B belonging to two different windows. Now, something called shifting of the window happens in the second block, and because of the shifting in the window, the pixels that were in two different windows in block number 1 may end up being in the same window in block number 2. And if you have pixels or patches in the same window, what happens? Attention score will be calculated between them, because that's what local attention does within one window. So that is how, although there is no global attention calculation, just by shifting, you can some kind of enable cross interaction between patches that were belonging to different windows in the first block. But by the time they reach the second block, they may belong to same windows. We'll see this. The shifted windows bridge the windows of preceding layer, providing connections among them that significantly enhance modeling power. This strategy is also efficient with regards to real-world latency. All query patches within a window share the same key set. What does it mean? I showed you 4x4 windows, right? I showed you a window in figure 1 which had 4x4 patches. So something like this, and like that 4 patches along the 3 more rows. Now, if this patch is the key, then all the window patches in the same window are the keys. Similarly, if this is the query, then all the patches in the same window are the keys. So basically, keys are all the 16 patches inside this window. Queries are also the same 16 patches inside the window. On the other hand, in contrast, earlier sliding window-based self-attention approaches suffer from low latency on general hardware due to different key sets for different query pixels. So there, what they were doing was, if this is a query pixel, they will construct a window around this pixel. So now this is the query. These pixels within this window are the keys. Now let's say this is my query, another pixel. Then the pixel surrounding that will be the keys. But here, look at this. If this is the patch, keys are all the 16 ones in this window. If this is the patch, keys are again the same 16 pixels patches in the window. So queries and keys are basically from the same window. Here, as the query changes, keys also changes in the sliding window. So this was the previous concept called sliding window. This is what they have in shifted window in Swin Transformer. And they are saying shifted window results in results in better latency, whereas sliding window results in low latency. Okay, suffer from low latency on general hardware due to different key sets for different pixels. Our experiments show that the proposed shifted window approach has much lower latency than the sliding window method. So basically, sliding window had certain amount of latency. I don't know here whether they actually mean to say low latency, or in contrast, earlier sliding window based self-attention suffer from low latency. I don't know whether they mean suffer from low latency or suffer from poor latency. I don't know what was the exact wording that they meant. In any case, the takeaway is that shifting window is faster and better, because the key query pairs are the same, are from the same window. In sliding window, as you look at another pixel as the query, the window that is drawn around that pixel, all the pixels inside that window will become the key. So as query changes, keys will change. Yet is similar in modeling power. So basically, shifted window approach has much lower latency than sliding window method, yet is similar in modeling power. The shifted window approach also proves beneficial for all MLP architectures. We'll see what they mean by this in the later section. The proposed Swin Transformer achieves strong performance on recognition tasks of image classification, object detection, and semantic segmentation. So these are the three, I would say, horsemen of image tasks, right? Detection, classification, segmentation. It outperforms Vision Transformer and Data Efficient Transformer, and it also outperforms ResNext models significantly with similar latency on the three tasks. In its 58.7% box average precision and 51.1% mask average precision on COCO dataset surpassed the previous state of the art by 2 We saw this in the abstract. Surpasses the state of the art by 2.7 percentage points and 2.6 for mask average precision. On ADE20K for semantic segmentation, it obtains 53.5 mean IOU. IOU means intersection over union on the validation set, an improvement of plus 3.2 mean IOU over the previous state of the art. It also achieves top 1 accuracy of 87.3% on ImageNet 1K image classification. So this is amazing. Basically, Swin Transformer is nailing every single three tasks. Task number 1 is classification, task number 2 is object detection, and 3 is segmentation. So, which is amazing. It is our belief that a unified architecture across computer vision and NLP could benefit both fields, since it would facilitate joint modeling of vision and textual signals, and the modeling knowledge from both domains can be more deeply shared. We hope that Swin Transformer's strong performance on various vision problems can drive this belief deeper in the community and encourage unified modeling of vision and language signals. So that is the introduction section. Now we will see a little bit of related work, and then after that we look at the architecture in detail. Related work, CNN and variants. CNN serve as standard network model throughout computer vision. While the CNN has existed for several decades, it was not until the introduction of AlexNet in 2012, this was the year it happened, that the CNN took off and became mainstream. Since then, deeper and more effective convolutional neural architectures have been proposed to further propel the deep learning wave in computer vision. Example, VGG, GoogleNet, ResNet, DenseNet. There are many other models also, EfficientNet, etc. HRNet. In addition to MobileNet, there are many models. In addition to these architectural advances, there has also been much work on improving individual convolution layers such as depth-wise convolution and deformable convolution. While the CNN and its variants are still the primary backbone architectures for computer vision applications, We highlight the strong potential of transformer-like architectures for unified modeling between vision and language. Our work achieves strong performance on several basic visual recognition tasks, and we hope it will contribute to a modeling shift. Self-attention based backbone architectures. Also inspired by the success of self-attention layers and transformer in NLP, some works employ self-attention to replace some or all of the spatial convolution layers in the popular ResNet. I'm not aware of these works exactly, 33, 50 and 80. Let me first quickly check which are those papers. 50 is, yeah, I think this Ramachandran et al. Paper was cited in the BERT paper, or rather in the Vision Transformer paper, it was highly cited. Then 33 and 80. So 33 is local relation networks for image recognition. Then 80 proceedings exploring self-attention for image recognition. So I guess there are many papers which have explored usage of self-attention for image tasks. I mean, Vision Transformer, Data Efficient Transformer, those are not the only papers. They just happen to be the most famous ones. In these works, self-attention is computed within a local window of each pixel to expedite optimization. So you consider one pixel, this is one pixel, this dot, and then you consider one window. Now this pixel will be the query that is attending to all the keys, which are all the other pixels inside this window. And they achieve slightly better accuracy / flops. Flop is floating point operations per second, flops trade-off. So basically, if accuracy is high and flops are low, it means you have a lightweight model with high accuracy. If the accuracy divided by flop ratio is very poor, very small, it means you have a heavyweight model with low accuracy, which is the worst case. They achieved better trade-off than the counterpart ResNet architecture. However, their costly memory access causes their actual latency to be slightly larger, significantly larger than that of convolutional networks. Instead of using sliding windows, we propose shifting windows. So this we discussed earlier, between consecutive layers, which allow for a more efficient implementation in general hardware. So instead of sliding window, shifting window. Self-attention or transformers to complement CNNs. Another line of work to augment a standard CNN architecture with self-attention layers or transformers. Another line of work is to augment a standard CNN architecture with self-attention or transformer. The self-attention layers can complement backbones. So 67, 7, 3. What are those papers? They have added 7 twice here. I mean, these small mistakes can always happen in papers. Not a big deal. 67 is this. What is that? The scamming hay was, I think, part of ResNet or something, right? He was the main author of ResNet paper, if I'm not wrong. Paper. Yeah, Scamming hay was the lead author. He's highly cited researcher, very, very famous. So that is 67. Then 3 and 7. What are those papers? I'm just checking if I know these papers beforehand. Most of these papers I probably haven't read. Attention augmented convolution networks, and 7 is non-local networks meet squeeze excitation networks and beyond. I haven't read these papers, just good to know their existence. By providing, can complement backbones or head networks by providing the capability to encode distant dependencies or heterogeneous interactions. More recently, the encoder-decoder design in Transformer has been applied for object detection and instance segmentation tasks. Our work explores the adaptation of Transformer for basic visual feature extraction and is complementary to these works. Here, basically, they are mentioning about some other works which used CNN and Transformer together. In this paragraph, they are mentioning about convolution entirely replaced with Transformer. Then transformer-based vision backbones. Most related to our work is the Vision Transformer, obviously, and its follow-ups. I'm sure follow-ups are data efficient image transformer, maybe some Wilbert, Visual BERT, etc. 63, 72, 15. Let me check some of these papers. 15 is, do we really need explicit position encodings? 60, then 15, 28, 63, 66. 28 is again transformer in Transformer. I haven't read this paper. I haven't heard of the paper at all, but I'm sure it's a good and famous paper. It's just that I haven't gone through it. Then 63, 66, 72. 63 is this training data efficient image transformer and distillation through attention. This is the DEIT paper, data efficient image transformer paper. 66 is a versatile backbone pyramid vision transformer, a versatile backbone for dense prediction. 67 is non-local neural networks. Then 72 is tokens to token vision transformer, training vision transformer from scratch on ImageNet. Okay, this is not the vision transformer paper. Vision transformer paper is different. Anyways, so those are the papers that they are citing here. The pioneering work of vision transformer applies a transformer architecture on non-overlapping medium-sized image patches. 16 by 16 is what they mean by medium. For classification, it achieves an impressive speed accuracy trade-off on image classification compared to convolutional networks. While vision transformer requires large-scale training datasets like JFT 300 million, this is Google's own dataset, to perform well, DEIT, data efficient image transformer, introduces several training strategies that allow vision transformer to be effective even on ImageNet 1K. This we have seen in the last. So DEIT uses a teacher-student model. Teacher is a bigger network, like it can be a CNN or bigger vision transformer. Student will be a smaller model. And then there will be knowledge distillation. There will be a distill token also. The results of vision transformer on image classification are encouraging, but its architecture is unsuitable for use as a general purpose backbone network on dense vision tasks, or when the input image resolution is high or something. Yeah, input image resolution is high due to its low resolution feature maps and quadratic increase in complexity. We know this. There are a few works applying vision transformer models to the dense vision tasks of object detection and segmentation by direct upsampling or deconvolution, but with relatively lower performance. So here they are mentioning about a couple of works which use vision transformer for denser tasks. Like classification is not a dense task, you can do with pixelated images, but object detection and semantic segmentation is dense task. You need more pixel information to actually segment or to actually detect objects. Concurrent to our work are some that modify the vision transformer architecture for better image classification. Empirically, we find our sim transformer architecture to achieve the best speed accuracy trade-off among these methods on image classification. So here they are mentioning about some of the past works and how Swin compares. Even though our work focuses on general purpose performance rather than specifically on classification. So general purpose means it should be able to do all the tasks: classification, segmentation, object detection, and it is able to do. So although their purpose is not to specifically build an architecture good at one of these tasks, it's a really good general purpose performance model. Plus on specific tasks, it is achieving state of the art. Another concurrent work explores a similar line of thinking to build multi-resolution feature maps on transformers. Its complexity is still quadratic to image size, while ours is linear. So that is another value proposition by Swin paper, and also operates locally, which has proven beneficial in modeling high correlation in visual signals. I don't fully understand this sentence, also operates locally, which has proven beneficial in modeling the high correlation in visual signals. I don't know, it's a broad sentence, but I'm sure it's explained very well in these papers. I don't want to spend too much time in understanding this one sentence because it's non-consequential in the rest of the paper. Our approach is both efficient and effective, achieving state-of-the-art accuracy on both COCO and object detection and ADE 20K semantic segmentation. So effective because accuracy is high, efficient probably because the accuracy to flops computation ratio is very good. So we'll see. I think that's what they mean by efficient and effective. So that's about the related work, and now let's get into the method section. Overall architecture. An overview of Swin transformer architecture is presented in figure 3. Figure 3 is in the next page. This is figure 3, the Swin transformer architecture. It looks a bit intimidating, but we will come back to this. Just keep this in your mind. It first splits an RGB image into non-overlapping patches by a patch splitting module like Vision Transformer. So basically an image of, let's say, something by 3. So 224 by 224 by 3, because there are RGB channels, are split into patches. So this is one image. One patch will be just like a small section covering all the 3 channels. Each patch is treated as a token. and its feature is set as a concatenation of the raw pixel RGB values. In our implementation, we use a patch size of 4x4, and thus the feature dimension of each patch is 4 times 4 times 3 equal to 48. So basically what they do is each patch is treated as a token, and its feature set is a concatenation of the raw pixel RGB value. So each patch has size 4 pixels by 4 pixel, and then it has also RGB. So every patch has 4 times 4 times 3 equal to 16 times 3 equal to 48 numbers. So every patch is a 48 dimensional token when you convert a patch into a token at the input. Then a linear embedding layer is applied on this raw valued feature to project it into an arbitrary dimension. So to convert a 48 dimensional vector to a C dimensional vector, so 48 dimensional vector, you can call it as what? 48 by 1 vector. You want to convert it into C by 1. For this, you can use a matrix whose dimensionality is C by 48. So if this is X, which is input, and if this is W, the matrix, and Y is the output, you can get W times X is equal to Y. So W will be C times 48, X is 48 times 1, so output should be C by 1, and it is indeed C by 1. So this is like a linear projection. So you will have bunch of neurons in the input, 48 neurons here. Then you will have output with C neurons, and the weights are these connections, which are projections going from 48 dimensional space to C dimensional space through these weights. Okay. A linear embedding layer is applied to this raw valued feature to project it into an arbitrary dimension denoted as C. Several transformer blocks with modified self-attention computation. These are called Swin Transformer blocks, whose diagram is given here. So this is a separate thing. Okay, so please don't get confused. I just want to draw so this, whatever is inside here is the Swin transformer block. This is not what is shown on this right hand side is not a succession of this, and this is inside this. The same thing is there inside this. This is there inside this. Same thing is there inside this, and inside this. Okay, that is how this architecture is, but we'll come to that. Slowly we'll come to that. Several transformer blocks with modified self-attention computation are applied on these patch tokens. Why do they say several transformer blocks? This is transformer block number 1. This is transformer block number 2, number 3, and number 4. And in all of these transformer blocks, you will have these two things, two successive Swin transformer blocks. Okay. So these are applied on your input image. So input image comes in here, height by width by 3 channels. Patch partition is done on that. Each patch is 4 by 4. So total number of patches is H by 4 multiplied by W by 4. And each patch will have 48 dimensions, and like that you will have H by 4 by W by 4 patches multiplied by 48, and then bunch of operations happen. Okay, now the transformer blocks maintain the number of tokens. So within one transformer blocks, so here as you go in here and when you come out here, the number of tokens are remaining the same. Number of tokens equal to total number of patches, which is H by 4 multiplied by H by 4. So here what goes in is H by 4, what comes out is H by 4. In the next blocks it is different, but within one transformer block the number of tokens or number of patches remain unchanged. And together with the linear embedding, it's referred to as stage 1. So stage 1 is this whole thing in this rectangle. So with linear embedding plus the Swin transformer block, those two combined forms the stage 1. We are yet to look at it in detail, so but I just want to give you an overview first. To produce a hierarchical representation, the number of tokens is reduced by patch merging layers as the network gets deeper. This we saw in figure 1. In figure 1, we saw that in the initial layers there were more patches, and then as you went up, the total number of patches decreased. The first patch merging layer concatenates the features of each group of 2 by 2 neighboring patches and applies a linear norm on the 4C dimensional concatenated features. What does this mean? It means if you have 4 patches like this, okay, and let's say each patch is of C dimensions. So this is patch number 1, patch number 2, number 3, and number 4. This has C dimensions, this has C dimensions, this has C, and this has C dimensions. What is done is all these 4 are merged into one single patch of 4C dimension. So that is what is done here. So 2 by 2 neighboring patches and apply a linear layer on the 4C dimensional concatenated vectors. So you apply a linear layer on these concatenated vectors to produce what? This reduces the number of tokens by a multiple of 2 by 2 equal to 4. 2x downsampling of resolution. So now the number of tokens now became, here you had 4 tokens because you had totally 4 patches, each of dimension C. Here you have 1 token of dimension 4C. Okay, so total number of tokens decreased by 2 times 2, decreased by a factor of 4. But here the patch dimensionality increase from C to 4C. Okay, and output dimension is set to 2C. Then what is done is, so earlier what was done was, if you had an image of 3 channels, so let's say this is 224 by 224 by C, you will divide this into 224 divided by 4 is what? 112 divided by 56, right? This will become 56 by 56 by each patch will be now 48 dimensional. So this channel dimension will be 48, something like this. Here it was 3 dimensional. So C was 3. Here C is 48. Then after the first transformer block, what will happen is, here 56 by 56 will become, you can divide again by 4, then it becomes what? 14 by 14. And one more thing was done, my bad. One more thing was done was, this 56 by 56 by 48 was projected linearly to become 56 by 56 by the number of dimensions for each patch was C. Then what was done after the first transformer stage is, 56 by 56 will become 14 by 14 and C will become 4C. So this depth dimension will become 4C. And then what is done is, this is projected into a 2C dimensional space using a linear embedding layer. So this will remain 14 by 14, but this will become 2C. So now can you see what happened? The spatial dimension reduced effectively from 56 by 56. It decreased to become 14 by, actually it's not 14 by 14. I think it's 28 by 28. This should not be 14 by 14, because each dimension is getting divided by 2. So this is my bad. So this will be 28, 28. This will be 28, 28. And this will be 2C. So now if you look at what happened, the spatial dimension, X dimension became reduced by 2, 56 became 28. This width dimension became 56 divided by 2, which is 28. This depth was 4C. It was C. It became 2C. So, but for that, it intermediate in the in-between stage, it went through a 4C dimensional channel size. Okay. So this is what they are saying in this sentence. To produce a hierarchical representation, number of tokens is reduced by patch merging layers as the network gets deeper. The first patch merging layer concatenates the features of each group. So 2 by 2, a neighboring set of 4 patches is concatenated into one single patch with 4x the number of dimension. Then that is became 2x number of dimension by going through a linear projection. Swin transformer blocks are applied afterward for feature transformation. So just like how Swin transformer was applied before, where it was h by 4 and h by 4, now it became h by 8 and h by 8. Why is it h by 8 by h by 8? Because 224 divided by 8 is 28, if I'm not wrong. So calculator, 224 divided by 8 is 28. Yeah. And 228 divided by 4 is 50. Oh, this was 57, is it? Sorry, 224 divided by 4. 56. Yeah. So this was your H and W at the input. This was H by 4 and W by 4. This was H by 4 and W by 4 and C. And this is what went through the stage 1 of the transformer. Then what goes through the stage 2 of the Swin transformer is this. This is H by 8, W by 8 and 2C. So, and this was H by 4, W by 4, C. So this goes through stage 1. This goes through stage 2. So this is what happens in Swin transformer. This first block of patch merging and feature transformation is denoted as stage 2, and then there is stage 3 and stage 4. So in stage 3, H by 8 will become H by 16, W by 16. I think 2C might become 4C if I am not wrong. I just want to see the image. Yeah, so here you have H by 4, W by 4, C. Here you have H by 8, W by 8, 2C. Here you have H by 16, W by 16, 4C. Here you have H by 32, W by 32, 8C. This is what goes through stage 1, 2, 3, 4. So you can see that in each stage, the spatial dimension X and Y both reduces by half. The channel dimension or the embedding dimension doubles in each stage. So C becomes 2C, 2C becomes 4C, 4C becomes 8C. So this is a classic thing which CNN also does. If you remember, in CNN in general, spatial dimension decreases as you go in stages. The channel dimension increases as you go in stages. Here it is not CNN, but effectively that's what's happening. Okay, and respectively, these stages jointly produce a hierarchical representation, which is clear, with the same feature map resolutions as those of typical CNNs like VGG or ResNet. As a result, the proposed architecture can conveniently replace backbone networks in existing methods for various vision tasks. Let me just erase some of these annotations so that we can maintain this thing a bit clean. Okay. All right. Okay, now let's read about the Swin transformer block. So what essentially happens to the image, just to reiterate, image, this is the input part, height by width by 3. Then patch partition will convert image into patches of size 4 by 4, which means total number of patches is H by 4 multiplied by W by 4. Like that, so this is number of patches, this product. 48 is the dimensionality of each patch. Then linear embedding will convert it from 48 dimensional patch to C dimensional patch, this linear embedding layer. Now H by 4 multiplied by W4, that many number of patches of dimensionality C will go through the Swin transformer block. By the time it comes out of the Swin transformer block, you will have H by 4, W by 4, C. The Swin transformer does not change the number of patches. What is Swin transformer block? Swin transformer block is this. It will have window-based multi-head self-attention and shifted window-based multi-head self-attention. We are yet to discuss this, but that is what happens inside here. But you can see this is classic transformer architecture. You have layer normalization followed by multi-head self-attention. So layer normalization, multi-head self-attention, residual. So this is the skip connection. Then again layer normalization, multi-layer perceptron, again residual. Then same thing goes through one more block of layer normalization, multi-head self-attention, but this is the shifted window multi-head self-attention, which we will discuss soon. And then you have a skip connection around the multi-head self-attention block, then layer normalization, multi-layer perceptron, right? So this is very, very similar to the normal transformer architecture. Then you might have a question, if it looks so simple and familiar, why did I say in the beginning that this part was tricky to understand, or this part is tricky to understand? In my opinion, in the whole paper, this is the hardest part to understand. To understand meaning not the concept, but its detailed implementation. This shifted window multi-head self-attention is one of the hardest things to understand. You might also be wondering, if we are converting or creating patches here, shouldn't there be some position embedding, token embedding, etc.? Where are those things? Token embedding, maybe you can imagine this projection from 48 dimensional space into C dimensional space. You can imagine that to be a token embedding, sure. But where is position embedding here? You should have that question, right? In none of these sections you explicitly saw any position embedding. So that is one question we have to answer. So what we have to discuss is, one, are we doing positional embedding, or where is it? Positional embedding. Then second is, why exactly is this complexity linear in Swin Transformer? That we are yet to discuss. Linear complexity. Third thing we have to discuss is the window-based multi-head self-attention. Fourth thing is shifted window-based multi-head self-attention. So if we can discuss these four things and understand it properly, we understand the whole paper. Okay. Now let's come to the Swin Transformer block. Swin Transformer is built by replacing standard multi-head self-attention module in a transformer block by a module based on shifted windows with other layers kept the same. A Swin Transformer block consists of a shifted window-based multi-head self-attention module followed by a two-layer multi-layer perceptron with JLU activation. A layer normalization is applied MSA as well as before MLP. This is normal, and a residual connection is applied after each module. So this we know. I mean, the only thing which we don't know here is what exactly is this shifted window multi-head self-attention. Now let's come to that shifted window-based self-attention. The standard transformer architecture and its adaptation for image classification both conduct global self-attention, where relationship between a token and all other tokens are computed. Meaning, if you have an image of 224 by 224 pixels converted into, let's say, patches of size 4 by 4, it'll be what? Each patch will be 56 by 56. Every single patch each patch is 4 by 4. There will be totally 56 by 56 patches. Every single patch will pay attention to every single patch in the image. So it's like a truly global self-attention in models like Vision Transformer, where the relationship between token and all the other tokens are computed. Global computation leads to quadratic complexity. This we saw earlier. I showed you the calculation with respect to the number of tokens, making it unsuitable for many vision problems requiring an immense set of tokens for dense prediction or to represent a high resolution image, because as the image resolution increases, as the number of pixels increase by X, the global attention computation complexity increases by X square. So this is the issue with shifted window. This is the issue with the normal vision transformer self-attention. Now, self-attention in non-overlapping windows. For efficient modeling, we propose to compute self-attention within local windows. So instead of considering self-attention inside the whole image, we consider it within local windows. Windows are arranged to evenly partition the image in a non-overlapping manner, supposing each window contains M by M patches. So now is the place where some visualization will actually help you a lot, because this is the part of the paper where, because of lack of good visualization, I was struggling a little bit. So I have created some visuals which I want to show you now. First, let us look at the quadratic scaling of Vision Transformer. This is easy, but I just want to show you this image. So if we have n tokens, whether it's an image or whether it's a text, you will have n queries and n keys, right? Because it's self-attention. So now the attention weights matrix will be n by n. So if you have 5 tokens, you will have 5 queries and 5 keys. So how many query key pairs you have? 5 times 5, 25. So if you have n tokens, the computational complexity of your attention score matrix will be n square. And then you take softmax of this and take a dot product with value. But let's talk about the attention scores themselves. Now let's say I have an image of 80 by 80 pixels, and let's say each patch is 16 by 16 in Vision Transformer. So total number of patches will be 5 by 5. So here there are total 25 patches, which means there are total 25 tokens. If there are 25 tokens, what is my attention complexity? It goes on the order of 25 square, because if I have 25 tokens, 25 keys are there, 25 queries are there. Between query key pairs, I have to construct attention. So 25 times 25, our attention complexity goes as 625, right? Now here, how many total pixels are there? I have HW, that many pixels. HW equal to 6400, right? 80 multiplied by 80. Now say I double my width and height, so total number of pixels is 4x. So if my width and height of the image increases by 2x each, total number of pixels goes by 4x. So now my number of tokens is what? 10 by 10, because each patch is 16 by 16. So this is one patch. And like that, I have 10 patches along the row and 10 patches along the column. So total, I have 10 by 10 equal to 10 multiplied by 10 equal to 100 patches. So now attention complexity will be on the order of n square. So what is square of 100? 10,000. So when my number of pixels went up by a factor of 4, so my number of pixels went from 80 times 80 to 4 times 80 times, 2 times 80 times 2 times 80, which is 4 times 80 times 80. So my number of pixels went up by a factor of 4. My attention complexity went up by a factor of 16. So as number of pixels became 4x, attention complexity became 16x. So 16 is the square of 4. So this is what we mean by quadratic complexity in the vision transformer. Now, how does it become linear in Swin transformer? Let's come to that. So vision transformer, I hope this part is clear. Number of tokens. So if width is the W is the width of the image, H is the height of the image, P is the number of, or P is the size of each patch. Total number of patches is W by P multiplied by H by P. And this is equal to N. Complexity is order of N square because N keys and N queries. So this part is clear. Now let's look at Swin transformer. What does Swin transformer do? Does it create attention between all the patches? It doesn't. It only creates attention within a local window. So now let's say this is my window. Okay. My window is 7 by 7 patches. Please note 7 by 7 patches, not 7 by 7 pixels. Each patch is 16 by 16. Let's go through this. So each window is 7 by 7 patches. Each patch is 16 by 16 pixels. And here again, one token is equal to one patch. And how many tokens are there inside this window? I have 7 patches multiplied by 7 patches, which is 49 patches I have inside my window, which is the window, this red color box. So what is the attention complexity inside that window? It is 49 times 49, correct? Because I have 49 patches total. Each patch is a token. Every token is a query. And since it is self-attention, those queries attends to those same tokens as keys. So query times key, I have 49 times 49 such multiplications. So attention complexity for the whole thing will be, let's try to calculate for the whole thing. Let's say my window size is 7 by 7. Height of the image is H, width of the image is W. Now I have how many, okay, this 7 by 7 is number of patches, okay, not pixels. So I have each window is a 7 by 7 patch, and total number of patches is H by P multiplied by W by P, correct? This is also the case, total number of patches. Now, each window will have how many patches? 7 by 7, which means every window will be 49 square. That many query key value pair dot products I'll have to do. Like that, how many windows are there? Total number of windows is equal to total number of patches along the row divided by windows along the row multiplied by, so total number of patches along the row is H by P, so or W by P. W by P number of patches are there along the width, and each patch is of width 7 each window is of width 7 patches, which means W by 7P. These many windows are there along the width, and H by 7P. These many windows are there along the height. So total number of windows is WH divided by 49P square. So total number of windows is this. For each window, this is the order of complexity of calculation. So total complexity of calculation is 749 square multiplied by WH divided by 49P square. And what is this? This is order of 49 WH divided by P square. So now compare this. So this is for Swin transformer versus for vision transformer. It was order of WH the whole square, correct? We did the calculation here. It was order of WH the whole square divided by P square. I mean, just to keep it consistent. This was the order of magnitude for vision transformer, the complexity. Here it is only linearly going with the image pixels. So WH is what? Total number of pixels along the width multiplied by along the height. That is the total number of pixels in the image. So for Swin transformer, the scaling of the complexity of the attention calculation is linear with respect to WH. For vision transformer is quadratic with respect to WX. I hope this is very clear. And why is it linear? Because I am looking at attention only inside one window. The total number of windows will be linearly proportional to the total number of pixels, but the size of each window is constant. Each window is like a 7 by 7 patch. Each patch is 16 by 16. So this is why Swin Transformer is called to be linear. So that is what we are discussing here. Let's come back to the paper. For efficient modeling, we propose to compute self-attention within local windows. The windows are arranged to evenly partition the image in a non-overlapping manner, supposing each window contains m by m patches. Please note, m by m patches equal to one window. It's not m by m pixels. Each patch could be 16 by 16 pixels. So now m by m was what? 7 by 7 in the example that we considered. The computational complexity of global MSA, which is multi-head self-attention module, and a window-based one is shown by this formula. Now this formula might appear confusing, but it's easy to kind of understand. So multi-head self-attention involves two things, right? One is calculating dot product between query and key and then taking softmax and value. But let's ignore the softmax part. Just taking query and key dot product, that is one calculation. To calculate query and key in the first place from your input, that is another calculation. So this is the complexity. So this is for the normal multi-head self-attention, like in Vision Transformer. This is for Swin Transformer to ease of understanding. So in multi-head self-attention for Vision Transformer, this is the complexity associated with calculating query and key. This is the complexity associated with calculating the dot products. Again, in Swin Transformer, this is the complexity associated with calculating query and key. This is the complexity associated with taking their dot products in pairs. Now let's see how do you get this. It's easy to do the calculation, but I have already set up it here from ChatGPT response. It's correct. So we can go through this. So let's go through step by step calculating the global multi-head self-attention complexity like in Vision Transformer. So first, complexity is associated with projecting input into query key value space, so that we need Q, K, V values. So query key value space is obtained by starting from a C-dimensional vector, right? Our vector is C-dimensional. And what comes out of the query key value is also C-dimensional. So at the end of the day, these matrices will be, you will have three matrices, one for WQ and one for WK and one for WV. And let's assume that it's just one attention head. Let's ignore multi-head attention. If it's just one attention head, the dimensionality, the matrix, each of these will be C by C dimensional. So you will have three such matrices. So cost for each token to create query, to create key, and to create value will be C square plus C square plus C square, which is 3C square. Like that, how many tokens are there in our image? The total number of tokens is equal to total number of patches. And what is total number of patch? Is small h multiplied by small w. What is small h? Small h is capital H by P. So h is equal to capital H by P. Small w is equal to capital W divided by P. So this is h is the total number of patches along the height. Small w is the total number of patches along the width. So total number of tokens equal to total number of patches is equal to h times w. So, and for every single token, I have to calculate this query key value. So total cost is 3hw c square. That is what is shown in the first, it's 4hw c square, but I'll show you where the last c square is coming. Apart from this, in multi-head attention, there is a projection layer, which again kind of mixes the inputs coming from different outputs coming from different attention heads. So this projection is basically another layer which projects from C-dimensional space to C-dimensional space. So there will be one more C square matrix for every single token. So that will be C square multiplied by HW. So 3C square multiplied by HW plus C square multiplied by HW, which will be 4C square HW or 4HC square. So this is the calculation involved with the first token. Okay, and this applies for both equally, for Swin Transformer as well as for normal Vision Transformer. This 4hwc square applies. Now please remember, small h and small w are not height and width of the image. They are the number of patches along the height and number of patches along the width. Okay, now what about the second term? Now computing the cost associated with calculation of attention weights. Q, which is the query matrix, I have how many tokens? I have HW tokens. Each token is represented by a C-dimensional vector. So Q has HW multiplied by C. This is the shape of Q. Key the shape of that is HW multiplied by C. So when you take dot product of this, it will be basically HW multiplied by HW. That will be the dimensionality of the query dot key transpose. Basically number of tokens along the row and same number of tokens along the column. So number of tokens is HW. So HW multiplied by HW. Then each element inside this query dot key transpose, which is the attention scores, each dot product is a product of is a dot product between C numbers. Why? Because query is a C dimensional vector, key is a C dimensional vector. So you are doing C calculations and adding them up, right, to get the dot product. So you have HW multiplied by HW multiplied by C, which is HW the whole square multiplied by C. That is the cost associated with calculating query dot key transpose. Then if we also include multiplication with value vector, this total number of calculation will double, because it is the final context vector is softmax of query times key transpose divided by square root of D multiplied by the value vector. Then this computation will double, because value has how many items? Value has you have each vector is of C dimensional, and you have HW such vectors. These are the total number of tokens. So you have HW number of total value vectors, each of dimensional C. So and then each of them are now you are taking a weighted sum of the value vector, attention weighted sum of the value vector, and you have to do that for every single query. So C times HW plus C times HW square plus C times HW square, which is 2 times HW square multiplied by C. So this is the second term here, 2 times HW square C. So the coefficient 2 or the C, those are not the important things. The important thing is the fact that you have a square here. HW is the total number of patches, which is proportional to total number of tokens, and HW square means square of the total number of patches or square of the total number of pixels. That is the important thing. That's a quadratic relationship. Now let's see how does it work for the Swin transformer. So in Swin transformer also, this calculation remains the same. 4HWC square remains the same, because you have to first get query key value before you calculate attention. So query key value anyway has to be calculated for every single patches, right? But now you look at one window for attention. Every window is M by M. And so every window is basically M by M patches or M by M tokens. Each token is of embedding dimension C. And how many such windows do you have? So M is the number of patches along the width of a window. M is the number of patches along the height of a window. Total number of patches along the height is H. So total number of patches along the height of a window is H by M. Total number of patches along the width of a particular window is W by M. So total number of patches, total number of windows. Okay, I let me just rephrase what I just said. This H by M thing. This is the number of patches along the row of a window. This is the number of patches along the column of a window. Now we want to know totally how many such windows exist. For that, we need to know how many patches exist along the height, that is small h. And each patch along the height, each window along the height is how many patches? It is M patches. So total number of windows along the height is H by M. Similarly, how many patches exist along the width? Small w. These many patches exist along the width. And how many patches constitute of one window width? M patches constitute of one window width. So these many windows exist along the width. These many windows exist along the height. And totally these many windows exist all together in your image, HW by M square. So HW by M square is the total number of windows, and you have M square token in every single window. So to take query dot key transpose, the query dot key transpose will be M square multiplied by M square. Why? Because along the row you will have M square tokens in the attention weights matrix. Along the column you have M square tokens. So totally you have M square times M square elements in your attention weights matrix, and every single item is a dot product of two vectors whose dimensionality is C. So you are doing C you are doing C multiplications. So that is m square times C within one window. So the computational cost for one window is m raised to 4 multiplied by C. Like that, how many windows exist in your whole image? Like that, HW divided by m square windows exist. So you multiply this m raised to 4C by HW by m square, resulting in HW times m square C. And you also now have to do softmax, and then after that you have to multiply it by value. So this whole thing becomes double, just like the previous example. So this becomes 2 times m square times HWC, and that is the second term of the Swin transformer, 2 times m square times HWC. And look at the scale. HW is the total number of patches, which is same as total number of tokens, which is proportional to total number of pixels, which is same as total size of the image. So here you are scaling linearly with respect to the size of the image. So this, if you look at this whole equation as a function of HW, if you call HW as X, let's say HW is equal to X. This is a linear equation because this is X times 4C square plus 2M square C. So this is a linear equation, the Swin transformer equation. On the other hand, this is a quadratic equation. This will be 4xc square plus 2x square c. So this is like a quadratic equation. This is the linear term of the quadratic equation. This is the quadratic term of the quadratic equation, or the square term of the quadratic equation. So this is why they say Swin transformer scales linearly with respect to the total number of tokens. And this is one of the biggest advantage, where former is the quadratic to patch number W. Former means vision transformer, and the later is linear when M is fixed. So M is set to 7 by default. Global self-attention computation is generally unaffordable for a large HW, meaning large number of patches or large number of pixels, while the window-based self-attention is scalable. Very good. Let's move on. Shifted window partitioning in successive blocks. The window-based self-attention module lacks connections across windows. So as I said, self-attention is calculated only within one window, which means a patch in window number 1 and another patch in window number 2, even if they are geometrically close to each other, they will pay no attention to each other, which is a problem, right? So because of these connections are lacking across windows, it limits the modeling power. To introduce cross-window connections while maintaining the efficient computation of non-overlapping windows, because non-overlapping windows make the computation of attention calculation linear, which is a good thing. But then if it is non-overlapping window and there is no cross-window attention calculation, it's a problem. So how do you solve this? For that, we propose a shifted window partitioning approach, which alternates between two partitioning configurations in the consecutive Swin transformer blocks. So shifted window partitioning approach, we'll see what that is, and that will basically explain this this part B in the figure, which is the twin transformer, Swin transformer blocks. As illustrated in figure 2, the first module uses a regular window partitioning strategy, which starts from the top left pixel and 8x8 feature map and is evenly partitioned into 2x2 windows of size 4x4. Let's see what this means. It's very easy. So every every image is divided into 8x8 feature map. So let me look at figure 2 first, because this paper is referring to figure 2 for the first time now, although figure 2 already appeared in one of the earlier pages, this one. So this is in the window based multi-head self-attention, the transformer block number 1. Let me write it as block number 1. And this is what happens in block number 2. So in block number 1, here you have 8x8 patches, 8 patches along the height and 8 patches along the row. Each patch is this gray color rectangle. Then you have every window is constructed using 4x4 patches. So totally you have 4x4 patches constructing one window, and like that you have 2x2 windows in one image. Totally 8x8 patches, and each patch is how many pixels? I'm not sure how many pixels makes one patch. I don't think they are mentioned. Maybe is it 8x8? Maybe it is 8x8 pixels per patch. No, I don't think that's the case. I don't think they have mentioned here in this paragraph, they have mentioned how many pixels make a patch. But anyways, then the next module adopts a window configuration that is shifted from the preceding layer. This is where the confusion starts, and I will show my figure, my version of the figure. So shifted window is, so in this block, in block number 1 and block number 2, what happens respectively are these two things. So this happens in block number 1. This happens in block number 2. In block number 1, you have windows like this, very clean, right? No shifting. In block number 2, some shifting happens. Now this image is a little bit confusing, but I will explain that with my own version of the figure in a moment. Let's just read a little bit more and then we'll come back to it. So as illustrated, there is shifting by displacing the windows by m by 2 pixels from the regularly partitioned windows. Okay, fine, but we'll come to that. We'll come to the figure, but let's finish this page. With the shifted window partitioning approach, consecutive Swin transformer blocks are computed using this formula. Do you think this is complex or easy? This is easy. I'll tell you why. Into the Lth layer of transformer block. So in the Lth layer of the transformer block, there are actually two blocks. One block with window-based multi-head self-attention and followed by that multi-layer perceptron. And in the Lth layer, you also have shifted window-based multi-head self-attention followed by multi-layer perceptron. In between, linear layers are there, and there is residual connection. So first, let us look at the Lth layer, window-based multi-head self-attention. What goes into the window-based multi-head self-attention is the output coming from layer normalization. The output coming from layer normalization is Ln of ZL-1. What is ZL-1? ZL-1 is the context vectors coming into the Lth layer from L-1th layer, correct? And that goes, and where is this shown in the figure? This one. So whatever comes from L-1th layer enters the layer normalization. Then whatever comes out of layer normalization goes into window-based multi-head self-attention. To that, residual is added, and that goes into layer normalization. That goes into multi-layer perceptron. Then there is residual added. This basically represented is represented as a formula here. So whatever comes out of L-1th layer undergoes layer normalization, and the output of that layer normalization is passed into window-based multi-head self-attention. To that, a residual is added, and what is the residual? Residual is the ZL-1 itself. So this plus is basically the residual. Now that is Z in the Lth layer cap. That is in the Lth layer, how does the context vector look after multi-head self-attention? Then this ZL cap goes into another layer normalization, which is just before multi-layer perceptron. So the output of that layer normalization goes as the input to multi-layer perceptron. And to the output of that multi-layer perceptron, you are adding a residual. What is the residual? Residual is the output coming from the window-based multi-head self-attention plus the residual, right? So this ZL cap is added as the residual over here. Then, so now this is what? This whole thing is the block number 1 in the Lth layer. And what is block number 1? The block with window-based multi-head self-attention. Block number 2 is block with shifted window multi-head self-attention. So then this output from block number 1 goes as the input into the linear layer normalization of the next block. So ZL, this guy, goes as the input here, and the output of layer normalization is the input to the multi-head self-attention. And what self-attention? Shifted window multi-head self-attention. And then you have residual. The same input that comes here is also added as residual. You can see the diagram. This formula is very straightforward. And then whatever comes out of the residual addition is noted as Z cap L plus 1. So they are denoting L and L plus 1. L because the transformer layer number L is window-based multi-head self-attention layer. The layer with L plus 1 has MLP and shifted window multi-head self-attention. And then again, L plus 2th layer will be, L plus 2 will be a window-based multi-head self-attention. L plus 3 will be shifted window multi-head self-attention, and so on. So this L plus 1th layer, this is the intermediate output. That intermediate output feeds into the layer normalization just before multi-layer perceptron. And to that, the same thing is added as a residual. And then now this is the output that comes from the L plus 1th layer. So now this is block 1, this is block 2, and block 1 primarily performs transformer block with window-based multi-head self-attention. Block 2 primarily performs implements transformer block with shifted window multi-head attention. So the reason why I have noted this as easy is, although it looks like a complex formula, it's literally that figure 2. It's showing figure 2, where ZL cap and ZL denote the output features of shifted window and MLP module for block L respectively. We know that. Let me zoom out a little bit. I'll read a little bit more before I explain you my next figure. My next figure is this. Although it looks like a simple figure, to reach this, I had to go through a lot of difficulties. Anyways, window multi-head self-attention and shifted window multi-head self-attention denote window-based and shifted window-based. Okay, this we understood. The shifted window partitioning approach introduces connection between neighboring non-overlapping windows in the previous layer and is found to be effective in image classification, object detection, and semantic segmentation. Now, so far, I found the paper okay, but this was the paragraph, these two. In this whole paper, the worst written paragraphs, in my opinion, are these two, because this is actually a dense section and they have compressed it into so little, it actually gave me a lot of struggles, these two. So before reading this paragraph, I will show you, let's say, a couple of things, and then I can come to this paragraph. That way your understanding will be easy. What exactly is this shifted window based self-attention? What exactly is it doing? So we have block number 1, which is regular window, block number 2, which is shifted window, right? In block number 1, what happens? What is this 0, 1, 2, 3? 0, 1, 2, 3 are windows. So tokens or patches inside window number 0 will not attend to tokens or patches in window number 1. So here A and B are two different patches belonging to window number 2. A and C are two patches belonging to two different windows. Although patch A and patch C are close to each other and patch A and patch B are close to each other, attention is created only between patch A and patch B because they are belonging to the same window. There is no attention scores calculated between patch A and patch C because they are belonging to different window. So this is what happens in regular window. Now, this once we move to the shifted window, what happens? In shifted window, they have shown a figure which looks something like this, right? So let me just take a screenshot of this figure 2, this figure, and I'll bring it at the place where I have my figure. So this same thing with shifted window, you can draw like this. So now window size I'm keeping the same. The only thing what I have done is the windows, instead of it perfectly wrapping like this, window is shifted by m by 2, and m is the width of one window. So this is m, this is m, and I am shifting every single window by m by 2. Why do I say m by 2? Because now this window, which was over here, shifted by m by 2 to the left and m by 2 to the top. So that window is now here. But one thing that has happened is to make, to wrap the whole image, I have to now have more number of windows. So here I had 2 by 2 windows, but here I have 3 by 3 windows. Only then I am able to wrap the whole figure. If I did not have this, I will not be able to wrap the whole figure. Window size is remaining unchanged, by the way. Window size I'm not touching. But this is how the wrapping happens. But this can introduce a few different problems, because when window size is increasing from 2 by 2 to 3 by 3, and assuming that I have some empty tokens, so this empty regions are some empty tokens, right? The total number of tokens go up from, let's say, proportional to being 2 square to 3 square. 2 square is 4, 3 square is 9. 9 is what? 4 times 2.25. So your calculation complexity will increase. Now let's see what's happening in this window. What is happening is called as a cyclic shift. So when this particular window, when this particular window shifts to the left, to left and top, what is done is this window, this window, this window, and this window are all assigned the same ID. Why? Because when originally this window was over here, actually let me take a square, that way I can draw it here. Originally that window was over here, and I am shifting this window like this to here. So the window originally that was here is being shifted here, right? So when something is going out of the image, something is going out to the left, you imagine it come back from the right, like a cyclic shift. So whatever comes out of the frame of the image is coming back into the frame of the image from the right. Whatever is going out of the frame of the image in the top direction, you imagine it to be coming back to the image frame from the bottom. So now think about what's happening. Something that is going like this out of the image will also come back into the image from over here, right? I don't know how much sense it is making, but let me explain you with the IDs. Okay, so let me delete this one more time. So what will happen is, here these patches, all the patches inside this window had ID 0, right? So if I had patch C, then C prime, C double prime, and C triple prime. So I have 4 patches inside this window. All those 4 patches belong to the same window of ID 0. Similarly, here let's say I have A, B, A prime, and B prime. I have 4 patches belonging to the same window of ID 2. Okay, and attention is constructed only among these 4 patches for this window, only among these 4 patches for this window. Even if A and C are geometrically close to each other, attention is not constructed between them because they belong to windows of different IDs. After shifting, what is done is, this 1/4 of this region of the image, or this whole patch or this whole window, is given the ID 0. This whole window is again ID 0. This whole window is of ID 0, and this whole window is of ID 0. Now, if you look at this patch, and this patch, they are geometrically far from each other. So in the regular window, they were not at all paying attention to each other because of 2 reasons. One is they are obviously geometrically far from each other. Second, they were belonging to different windows. These 4 patches were belonging to completely different windows. Window number 0, 1, 2, and 3. In the regular window, these 4 patches, and see, please don't get confused when I say patch and window. Patches construct windows. So within one window here, you have 4 patches. And this ID, I'm not IDing the window. I'm not IDing the patch here. I'm IDing the window here. So the 0, 1, 2, 3 are the IDs of the window. A, B, C, D are the IDs of the patches. So I'll have one patch which was this, one patch which was this, one patch which was this, and one patch which was this. In regular window, this patch was belonging to window number 0, window ID 0. This patch was belonging to window ID 1. This patch was belonging to window ID 2, and this patch was belonging to window ID 3, which means those 4 windows never paid attention to each other in the regular window. But now look at it in shifted window. In shifted window, their window ID are the same. It's all 0, which means those are the 4 patches which will pay attention to each other in window number 0. Now let's look at one more example. Look at the patch number A and patch number B. Geometrically, they are next to each other. And they were paying attention to each other in the regular window. Why? Because patch number B was this guy. This was patch number, maybe I can call it as a different name, but this was patch number B here, and this was patch number A. They were neighbors, plus they were from the same window, window number 1, and they were paying attention to each other in the regular window. Now in shifted window, although A and B are neighboring patches, there is no attention between them. However, patch A and patch C in this example, they are belonging to the same window ID number 2, which means although they are geometrically far from each other, they are paying attention. So now just zoom out a little bit and look at what's happening. In regular window, attention scores are constructed in general between actual pixels that are close to each other, right? Because windows are regular windows, within one window, pixels are close to each other. They are paying attention to each other. In shifted window, but now look at this. The patches are geometrically far away, but they are still paying attention to each other because their window ID remains the same. So in shifted window, you cleverly allow the patches, although they are geometrically far away, you allow them to pay attention to each other. And this is how you kind of do mixing. So originally, if you look at these 4 patches, this, this, and this. Those 4 patches were in completely 4 different windows, window number 0, 1, 2 and 3. But now look at that in the shifted window, all those 4 patches are in window number 3. So see, those 4 patches that could not interact with each other in regular window are now able to interact with each other in shifted window. These 4 patches in the corner, which were farthest away in the regular window, are now in the same window, in the shifted window. Same window meaning same window ID number 0. Similarly, this patch number, these 2 patches in the window number 1 and these 2 patches in window number 2, they were again vertically far away, but now they are paying attention to each other because now their window ID is the same. So this is basically what shifted window does. Now you might have a question. How do you in practice implement this? How do you in practice implement the idea that, although these 2 are geometrically close to each other, they should not pay attention to each other? How do you in practice implement it? We will look at that. But I hope you get this idea, because this is most important concept in the paper. In regular window, the proximity of the patches primarily determines their attention, although it has to be limited to the same window. In shifted window, the patches need not be physically close to each other. The patches can be far away, but their window IDs will remain the same, can remain the same. And based on that, they can pay attention to each other, right? So this is the primary idea between regular window and shifted window. Now let's read the paper. There is one more important detail which I haven't mentioned yet, which is position embedding. Where is position embedding coming? Because patches need some position information, right? We have not discussed anything about position embedding. In Vision Transformer, we discussed that position embedding can be simply sequence of like 2-dimensional position function constructed, or it can be a learnable position embedding. What about here? What about in Swin Transformer? What is position embedding? Let's discuss that a little bit now, and then let's read that particular section annotated in the paper as difficult to understand. So in Swin Transformer, the position embedding is actually not added before going into the transformer multi-head self-attention. It is added within. So attention weight between query and key, right? If we denote it by alpha ij, where I is the query and j is the key, this is how it is calculated. Alpha ij equal to softmax of, usually it is just softmax of query times key transport divided by square root of d. This extra b is not there. But bij is the relative position bias between ith query and jth key, which are basically patches inside a window. So this is how position information is injected into the calculation. Usually what is done is, during the input embedding itself, right after input embedding, position is added to input embedding, right, as a same dimensional vector. But here it is added as a bias term. So this is called as a relative position bias term. So this is what happens in the normal transformer block. Normal meaning the normal window. In shifted window, the equation is slightly different. There is one more term. The one more term is mask ij. Can you guess what is this mask ij? Mask ij is, if you are normally dividing the image by saying patches from 0, 1, 2, 3 up to 6, they are belonging to the same window along the row, and along the column also patches 0 to 6 belong to the same window. If you say like that, it is true in the regular window, but it is not true in shifted window, because in shifted window, the first top left, in shifted window, the top left is basically something like this. This is the top left corner. And here 4 patches are literally belonging to 4 different windows. So then what is done here is an additional masking term is introduced called mask ij, where mask ij value is 0 if the query I and key j, meaning the patch number I and patch number j that are trying to attend to each other, if they are belonging to the same, if they have the same window ID, the mask ij term is 0. Because if they are belonging to the same windows, you can do the calculation just like the regular window, not like the shifted window. But if they are belonging to 2 different windows, meaning if they are 2 tokens that are trying to attend to each other, but they have 2 different window IDs, then what you should do, you should prevent it, right? Then they should pay 0 attention to each other. So final output alpha ij should be 0. And softmax of what is 0? Softmax of negative infinity is 0, because in softmax calculation there is an e raised to x term coming. If e raised to x is equal to e raised to minus infinity, then it will be 0. So then what can you do? You can simply say if I and j are two patches belonging to two different windows with different IDs, assign mask equal to negative infinity. In Python, when you implement, you will say mask ij is minus inf. That ensures that when you take the softmax, this alpha ij, which is the attention score between those key query pairs, will be 0, because they should not pay attention to each other. Why? Because they belong to two different windows. But the relative position bias term remains the same. So this is one detail which is very difficult to understand from the paper. It's called as position bias and not position embedding, because usually in position embedding, the position embedding information is added directly to the token before the query key value production. But here position information is injected after calculating query key value, just before calculating the attention scores, right? So that is why Swin Transformer model utilizes or does it differently compared to Vision Transformer. Now, how do we construct position embedding bias or position bias? Think about each window. Each window has 7 by 7, which are 49 patches, correct? And each patch will attend to every other patch. So ideally, how many positions are there? Unique position terms are there. 49 times 49. What is this number? 49 times 49. 2401. So 2401 unique query key value pairs are there in any given window, correct? So does it mean that for every single one of those pairs, you need to construct one unique position bias? So are you saying that we should have 2401 different position bias terms? No, it is not needed. The reason is, in position bias, we don't care about the absolute position. We only care about relative position. Let's say I have one patch over here and this patch is trying to attend to this patch. What's the relative position of this patch with respect to this? Delta x is equal to, let's call it as 1. Basically, it's jumping by one position. Delta y is equal to 0. In y-axis, it did not jump. What about these two patches? This patch has a relative position of delta x equal to 1. Delta y equal to 1. What about if I'm looking at this patch with respect to this patch? I have to jump 2 times in the negative direction, right? So delta x equal to negative 2, delta y equal to 0. So how many such unique delta x, delta y values would be there in my window? First of all, think about my window. My window size m equal to 7, which means maximum distance between two patches along x will be delta x is equal to maximum positive number will be plus 6, minimum number, negative number will be minus 6. Similarly, maximum positive y number will be plus 6, minimum negative y number will be minus 6. So this is a set of 13 numbers ranging from minus 6 to plus 6. This is a set of 13 numbers ranging from minus 6 to plus 6. So if you look at the offset, relative offset between two different patches within a window, and if you describe that offset by a delta x, delta y pair, how many such unique delta y pairs can you construct? You can construct 13 by 13 equal to 169 pairs you can construct. 13 because delta x can be 13 unique values, delta y also can be 13 unique values. So instead of constructing 2401 unique bias terms, you just need to construct 1169 unique bias terms. Now these bias terms, the value of these 169 terms will be learnable, meaning it is not something that we define, it's learnable. But once it is learned, you store it in a table. Like you will have a table with 169 items. And depending on what delta x, delta y values you have, you look at the table to fetch the appropriate bias term, right? So this is an example. If you look at the displacement delta x equal to 1, 0, that means one patch is directly to the right side of the other patch. Like that, there are many pairs which are to the right of each other, right? Patch number 2 and patch number 3, they are to the right of each other. Patch number 5 and 6, they are to the right of each other. Patch number 6 and 7, they are to the right of each other. So attention basically between these patches is based on their proximity and we can use this relative displacement between them. We don't need the absolute displacement. So these are some examples of pairs that share the same displacement. So patch number 0, 0 and 1, 0, they are displaced by a factor of 1 along x-axis. 1, 0 and 2, 0, they also have this same displacement. These two pairs also have same displacement. These two pairs also have same displacement. So they all should share a single positional bias value. So what this means is, positional bias, you don't have to calculate different positional bias value for all the different patch pairs. You just need to calculate it based on their relative displacement, and relative displacement between many different patch pairs are the same. So instead of 2401 different position bias values, you just construct 169 position bias values, and then you store it in a table. So that is essentially the position embedding. Okay. Now let's come back to the paper and read the sections that we have marked as kind of difficult to understand, this black color region, and let's now read it with our current understanding. Efficient batch computation for shifted configuration. An issue with shifted window partitioning is that it will result in more windows in the shifted configuration, and some of the windows will be smaller than m by m. We saw this for the corner windows or the top window, bottom window, right window, they were smaller. Where is my image? So this window essentially is smaller. The patches, there are only 2 patches in this window. This window essentially is smaller. This is smaller. So only one window has 4 patches. Remaining windows have either 2 patches or 1 patch. That was one thing. Plus the number of windows increased. Instead of 2 by 2, it became 3 by 3. A naive solution is to pad the smaller windows to a size of m by m. So padding meaning you simply pad with some empty pixels. So here you add padding of empty pixels, here you are adding padding, here you add padding. Then you say these 4 are belonging to the same window, these 4 belong to the same window, these 4 belong to the same window. But then the problem is your computation increases, plus there is no cross attention between this and this. So it kind of defeats the purpose of having Swin Transformer altogether. So a naive solution is to pad the smaller window and mask out the padded values when computing the attentions. Sure, the padded values you can mask. When the number of windows in regular partition is small, that is 2 by 2, the increased computation with this naive solution is significantly higher, because now you have 3 by 3 windows. So instead of 4 windows, you're considering 9 windows. Hence, here we propose a more efficient batch computation by cyclic shifting. Cyclic shifting is why the left hand top corner item, right hand top corner, left hand bottom corner, and right hand bottom corner, they all became of window ID 0. So that is because of the cyclic shifting. After the shift, a batched window may be composed of several sub windows that are not adjacent in the feature map. You saw that the sub window 0, number 0, sub window number 0 on the top right, sub window 0 on the bottom left and bottom right. They are actually not adjacent in the feature map, but those 4 sub windows make the window number 0. So a masking mechanism is employed to limit self-attention computation to within each sub window. Basically, if every patch will have a window ID associated with it, if the window ID of 2 different patches are the same, there will be attention between them. If the window ID between 2 patches are not the same, they will have no attention between them, right? That is how it is done. With the cyclic shift, the number of batched windows remains the same as that of regular window partitioning. So number of windows will still remain 2 by 2. And this will be more efficient. The low latency of this approach is shown in table 5. So this results in much lesser latency. This is the shifted window implementation. And now let's come to relative position bias. In computing self-attention, we follow these papers by including a relative position bias. So this is the relative position bias term, where a query key value is like m square by d. So it's d-dimensional space. M square is the number of tokens or the query key value. D is the query key dimension. M square is the number of patches or number of tokens. Since the relative position lies in the range of minus m plus 1 to m minus 1, so basically it was ranging from minus 6 to plus 6, which was minus 7 plus 1 to 7 minus 1. We parameterize a smaller sized bias matrix, and values in B are taken from this table. Basically, it's a learnable bias value table. Inside those table, there will be 169 values. Those if m equal to 1, then from those 169 values, you will pick whichever is appropriate value depending on the delta x value and delta y value. But look at the way it is written. It's very, very difficult to understand. I really challenge you to first read this and try to understand it. It's very difficult. Unfortunately, this is the least favorite part of my this paper for me. we observe significant improvements over counterparts without this bias term. So if bias term was absent, meaning no position information was added, compared to that, there is significant improvement. And when they say significant improvement, don't expect like 10-20% improvement. Like it's just 1-2% improvement. Okay. In computer vision, that is the big, that 1-2% is considered very big. Further, adding absolute position embedding to input drops performance slightly, thus it is not adopted. So you could have done absolute position embedding also, just like how Vision Transformer does, but it seems to reduce the performance. So in this paper, they use relative position bias. The learned relative position bias in pre-training can be also used to initialize a model for fine-tuning with different window size through bicubic interpolation. So basically, if your number of windows are more, or number of patches inside a window are more, then you may have, let's say, 15 by 15 window size, let's say. Then you have numbers going from -14 to 14, which is 29. Then you will need a bias table. Instead of 13 by 13, you will need a 29 by 29 bias table. But you can construct that bias table from the 13 by 13 bias table through bicubic interpolation. Alright, so that is the detail about two things. One was shifted window and one was relative position bias. And I hope when you spend more time on this part of the paper, you will understand it more and more. And if any doubt, you just watch my section where I explain this part, okay? It's actually a simple concept, but unfortunately the way it is written is very complex. It's making it very complex. Okay, now let's move on to architecture variance section and experiments section. So at this point, I felt like taking a break. So I took a break and I'm continuing the paper dissection after a break of few hours. I recommend you also to do the same if you feel a little bit tired, or if you feel a bit, I would say, you are saturated in your mind. But anyways, let's continue our review. We'll be moving to section 3.3, architecture variance. We build our base model called Swin B to have the model size and computation complexity similar to Vision Transformer B. So Vision Transformer also had base large and one more model, small, I guess, to Vision Transformer or data efficient image transformer B. We also introduced Swin T, Swin S, and Swin L, which are versions about 0.25x, 0.5x, and 2x the model size. Model size meaning 2x, I guess, the base size, and computational complexity respectively. Note that the complexity of Swin T and Swin S are similar to that of ResNet 50 and ResNet 101. The window size is set to m equal to 7 by default. The query dimension of each head is d equal to 32. And the expansion layer of each multi-layer perceptron is alpha equal to 4. So the projection in the multi-layer perceptron is 4x the dimensionality of the input embedding for all experiments. The architecture hyperparameters of these model variants are Swin C equal to 96, layer numbers 2262. So 2262 means, if you look at the architecture over here in figure 3, this is repeated 2x, this is repeated 2x. So 2x means one regular window and one shifted window. This is 6x and this is 2x. So 6x means there will be 3 regular windows and 3 shifted windows alternately. So 3, one after the other, regular, shifted, so on. So here they are giving those numbers, I guess. Layer numbers 2262, 2218, 2218, 2218. It's very difficult for me to say why exactly it is 2262 and why not 2622, or why not something else. So I guess it's a result of their experiments. I'm sure they have tried many other variations and found out these to be the best. Where C is the channel number of hidden layers in the first stage, the model size, theoretical computational efficiency, complexity in flops, and throughput of the model variants for ImageNet classification are listed in table 1. We look at table 1 when we reach that page. Now, section 4, experiments. We conduct experiments on ImageNet 1K for image classification, COCO object detection, and ADE 20K for semantic segmentation. So ADE 20K is this data set. It's from CSAIL Computer Science and Artificial Intelligence at MIT. And it has the full data set is over here. Training data set has 25,000 plus images. Validation is 2,000. And test is, I guess, the rest of the, or similar number of images perhaps. But these are the kind of images for segmentation. And actually, I don't know what these are, probably from internet. But anyways, this is hosted on CSAIL website, MIT. So that is used for segmentation, semantic segmentation. In the following, we first compare the proposed Swin Transformer architecture with the previous state of the arts for the three tasks. Three tasks meaning classification, detection, segmentation. Then we ablate the important design elements of Swin Transformer. Okay, now first task is image classification on ImageNet 1K. For image classification, we benchmark the proposed Swin Transformer on ImageNet 1K, which contains 1.28 million training examples and 50K validation images from 1000 classes. The top one accuracy on a single crop is reported. We consider two training settings. So first is regular ImageNet 1K training. In this setting, we mostly employ Adam W optimizer for 300 epochs and cosine decay learning rate scheduler and 20 epochs of linear warm-up, a batch size of 1024, initial learning rate of 0.001, and weight decay of 0.05. We include most of the augmentation and regularization strategies of 63. I think 63 is data efficient image transformer. I just need to check once, because they had an extensive set of regularized data augmentations applied. Yeah, so that is the data efficient image. Yeah, this one, training data efficient image transformers and distillation. Yeah, so it's a DEIT paper. Then except repeated augmentation. So you do the repeated augmentation and EMA. I don't know what is this EMA. We can ask ChatGPT. This is from Swin Transformer paper. What is in this context? Oh, I think I lost my screenshot. This is from Swin Transformer paper. What is EMA in this context? Exponential moving average. All right. Which do not enhance performance. So those augmentations do not enhance performance. These are anyway experimental details which we don't have to spend too much time on, but it'll be good to be aware of those. Note that this is contrary to 63, which is the data efficient image transformer, where repeated augmentation is crucial to stabilize the training. Then pre-training on ImageNet 22K and then fine-tuning on ImageNet 1K. We also pre-train on larger dataset ImageNet 22K, which is 14.2 million images and 22K classes. We employ Adam W optimizer for 90 epochs using linear decay learning rate scheduler with a 5 epoch linear warm-up, a batch size of 4096, and initial learning rate of 0.001, and weight decay of this is used. In ImageNet 1K fine-tuning, we train the models for 30 epochs with a batch size of this, learning rate of this. Okay. Results with regular ImageNet training. Table 1A presents comparisons to other backbones, including both transformer-based and ConNet-based using regular ImageNet 1K training. Compared to the previous state-of-the-art transformer-based architecture, that is DEIT, Swin Transformers noticeably surpass. So this is the result of the first thing, where you are directly training on 1K. Second one will be directly training on ImageNet 22K and then fine-tuning. So table 1, we'll see table 1 in detail, but compared to previous state-of-the-art, that is DEIT, Swin Transformer noticeably surpasses the DEIT with similar complexity, like 1.5% for Swin Transformer, basically 1.5% improvement over DEIT small. So they are comparing similar architecture, not the exact state-of-the-art. And this much compared to Swin B, and over Swin B has 83.3 and 84.5 over data efficient image transformer B using image of size 224 versus an image of size 384. Compared with the state-of-the-art ConNets, that is RegNet and EfficientNet, the Swin Transformer achieves these two. RegNet and RegNet and EfficientNet were used in data efficient image transformer also to compare against. The Swin Transformer achieves slightly better speed accuracy trade-off, noting that while RegNet and EfficientNet are obtained via a thorough architecture search, this is true because this is achieved through a neural architecture search, NAS. The proposed Swin Transformer is adapted from the standard transformer and has strong potential for further improvement. So let's look at the table 1 quickly. So regular ImageNet. So this is just the ImageNet pre-training to a 1K model. This is the ImageNet 22K pre-training followed by 1K fine-tuning. Okay, so in RegNet, if we just look at the ImageNet accuracy, it's 80, 81, 87, etc. So Swin base has 83.5 and 84.5 for the two image sizes. Data efficient base has this, so this is definitely better. Vision transformer base is less efficient at B3 or rather B6, B7. They are 84 and 84.3, but they are trained on much bigger images. You see 528 image size, 600 as the image size. But if they are trained on 300 image size, then it's only 81.6, and that is lower than Swin Transformer. I'm just comparing comparable models. If we do pre-training on 22K, then we compare against similar models. Swin Transformer base model 85.2, Vision Transformer base is 84. Then 384 image sizes is R101. I guess this is ResNet 101, 84.4. So here also again Swin Transformer is better. So you can see that, and here actually the image size is significantly smaller. One more thing we can look at is throughput, which is images per second. You want more images processed per second. So Swin B on 224 image has 278.1 as a throughput. Data efficient image transformer B has 292.3. So throughput, data efficient image transformer B has slightly better throughput, I guess. And efficient net B6, B7, or rather here, this one. Okay, this one has very good throughput, but it has low accuracy. Let's read this section, then we'll understand better. Results with ImageNet 22 pre-training. We also pre-trained the larger capacity Swin B and Swin L on ImageNet 22K. Results fine-tuned on ImageNet 1K classification. For Swin B, ImageNet 22K pre-training brings around 1.8 to 1.9% gains over training on 1K dataset from scratch. Compared with previous best results for ImageNet 22K pre-training, our models achieve significantly better speed accuracy trade-off. Swin B obtains 86.4% top-run accuracy, which is 2.4% higher than Vision Transformer of similar throughput. And this is the comparison of speed. So speed through a Vision Transformer is slightly faster, but not too much, not by too much, and slightly lower flops, 47 gigaflops versus 55.4 gigaflops. So the flop is basically the floating point operations needed. So this one has flops is given in this column, and Swin base has 47 gigaflops for the 384 model, and here for the 384 model it is 55.4 gigaflops. So the lower the flops, the better, because lower the number of floating point operations required for the model, the better it is, because it's more lightweight that way. So that is the case here. Okay, that's it. Then so this is about image segmentation. So clearly Swin base model is reaching the state of the art. Swin large has surpassed everything, 87.3% accuracy. Then object detection on COCO. Object detection and instance segmentation experiments conducted on COCO 2017, which contains 118K training, 5K validation, and 20K test dev images. An ablation study is performed using the validation set, and a system level comparison is reported on test dev. For the ablation study, we consider 4 typical object detection framework: Cascade Mask RCNN, ATSS, Rep Points V2, and Sparse RCNN. I know what is RCNN. I just want to see what are the rest of the things. What are these models? Models or frameworks. Object detection framework: Cascade Mask RCNN, multiple cascaded head, adaptive training sample selection, Rep Points V2, Sparse RCNN. I don't want to go into the details of this because it will derail us from the progress in the paper. Let's just understand that these are different frameworks for object detection. In these 4 frameworks, we utilize the same setting, multi-scale training, resizing the input such that shorter side is between 480 and 800, while longer side is at most 1333. Adam W optimizer, weight decay, so these things are fine. I just want to see the results. We compare our Swin Transformer to standard coordinates and ResNext and previous transformer networks DEIT. The comparison are conducted by changing only the backbones with other settings unchanged. Note that while Swin Transformer and ResNext are directly applicable to all the above frameworks because of their hierarchical features, DEIT only produces a single resolution of feature maps and cannot be directly applied. For a fair comparison, we follow 81 to construct hierarchical feature maps for DEIT using deconvolution layers. So now there are a bunch of tables here which show the accuracy comparing the method used in this paper, which is Swin Transformer, and the rest of the papers. So here there are various frameworks compared. Method is Cascade Mask RCNN in this case, and backbone is if it is ResNet 50 versus Swin Transformer, or I don't know if this is ResNet 50 or RCNN. Here Swin Transformer has 50.5. Let me ask, what is R50 here? What is R50? Okay, ResNet 50 backbone. All right. So you can see that Swin has better average precision. AP means average precision at different recall values. So you construct precision recall values and then you take an average of precision over different recall values. Let's not go into the details of object detection because that we have done in various other bootcamps on our channel, but just understand that Swin is universally good at various image tasks, including classification, detection, and segmentation. Comparison to ResNext. Table 2 lists the results of Swin T and ResNet 50 on 4 object detection framework. Our Swin T architecture brings consistent box average precision gains over ResNet 50. This we saw from the current table with slightly larger model size, flops, and latency. Table 2b compares Swin and ResNext under different model capacity using Cascade Mask RCNN. Swin Transformer achieves higher detection accuracy of 51.9 box average precision and 45 mask average precision, which are significant gains of plus 3.6 and plus 3.3 respectively over ResNext. So ResNext next as a model, it has higher flops, floating point operation, and higher latency. On a higher baseline, this is fine. I just want to see, basically Swin, they have given it in bold. So Swin is outperforming all the other ResNext models compare in all the different tasks. And those models have higher flops. So 889 gigaflops, 739 gigaflops. So compared to data efficient DITS or ResNext 101, I think here actually Swin has higher number of flops, I guess. Frames per second is higher, but flops is higher for Swin Transformer parameter. So it's almost comparable. It doesn't make sense to compare it exact number by number, but it's almost comparable models in terms of size and speed. Okay, comparison to DEIT. Performance of DEIT using the Cascade Mask RCNN framework. Results are, again, Swin Transformer is better. That is all right. Comparison to previous state of the art in table 2C. Where is 2C? This is, I guess, 2C. And you can see that Swin Large is performing the best in AP average precision, box average precision, and mask average precision for both. But other than that, I don't think it teaches us a lot of things to just read this table. Let's not spend too much time on it. I'm not too curious about the details of the table as such. Then semantic segmentation on ADE20K. ADE20K is widely used semantic segmentation dataset covering a broad range of 150 semantic segmentation categories. It has 25K images in total, 20K for training, 2K for validation, another 3K for testing. All right. We utilize UpperNet and segmentation as our base frameworks for its higher efficiency. And I'm in the results in table 3. Where is table 3? This is table 4 and 5. This is table 3. Here you can see that the best performing model is UpperNet framework and Swin large model. It achieves the best mean IOU score for validation and testing. Anyways, that's the main conclusion. We don't have to go through the details right now. Then ablation study. In this section, we ablate important design elements in the proposed Swin transformer using ImageNet 1K classification, Cascade Mask RCNN on COCO, and UpperNet on AD20K. Then shifted windows. Ablations on shifted window approach on the 3 tasks is shown in table 4. So Swin transformer with the shifted window partitioning outperforms the counterpart built on single window partitioning at each stage. So shifted window versus single window. So without shifting, this is with shifting. So without shifting consistently achieves lower accuracy. This is the regular window, but shifting means it can learn cross window patterns, right? The attention, there is effectively there is cross window attention when we shift the windows. So that is the reason why without shifting is better. Then I'm sure this is about position, relative position bias, but let's read that section first. The latency overhead by shifted window is small as shown in table 5. So let's see the latency overhead after shifting window. So sliding window has very high latency, as we know. Sliding window is the naive operation, or sliding window was the original operation. Shifting window is the current one, and shifting window has very low latency in terms of milliseconds. That is what this table 5 is. Yeah, shifted window with padding and cyclic shifting window. So padding is the naive operation. Shifting window with cyclic, cyclic, I would say, moving of the windows from, if you shift something to the top, whatever goes out of the frame comes back up from the bottom. If you shift something to the left, whatever goes out of the frame comes back from on the right. So that is cyclic shifting. You can see that the latency, I don't know what S1, S2, S3, S4 means. You can ask GPT. What does S1, S2, etc. mean here? Four hierarchical stages. Okay, stage 1, stage 2, the amount of latency in each stage, I guess, in milliseconds. Okay, I understand that. Slowest because it processes largest number of tokens. Yeah, right, number of tokens decrease as you go from one stage to the next. So this also we know. So now let's look at relative position bias. This was one area of confusion for us, like why not normal position embedding? Why do we have relative position bias? So table 4 shows comparisons of different position embedding approaches. Swin T with relative position bias leads plus 1.2% top 1 accuracy in ImageNet, and mask average precision. So these are the position embedding, no position embedding, absolute position embedding, absolute plus relative. So absolute means I think it's adding position embedding right after tokenization. Absolute plus relative means adding position embedding after tokenization plus also adding relative position bias. Relative position bias without appending. What does this mean? I don't understand. What does relative position embedding without mean? Relative position embeddings are added after attention as a separate term, not applied inside the attention score computation. Oh, I see. So instead of having the position bias added inside the softmax of query times key transpose divided by square root of d plus bias, instead of doing that, put it after calculation of alpha ij, like a separate term. Okay. In Vision Transformer, it's not, that is not what is done, right? In Vision Transformer, position embedding is added during the tokenization, just after token embeddings. They do not use relative, but they do not apply it inside the attention logits. Yeah, this is how normally Swin does. It adds a position bias, but yeah, anyways. So the final takeaway is that the relative position bias, which is done in Swin Transformer, that gives the best accuracy for 3 tasks, for classification, detection, and segmentation. So these are the 3 columns: classification, detection, and segmentation. Okay. and it achieves in relation to those without position embedding and with position embedding. All of this is fine. While the recent vision transformer and data efficient image transformer model abandoned the translation invariance in image classification, even though it has long been shown to be crucial in visual modeling, we find that inductive bias that encourages certain translation invariance is still preferable for general purpose visual modeling, particularly in the dense prediction task of object detection and semantic segmentation. Here, my only thing is, where exactly are they bringing inductive bias? Maybe they are bringing inductive bias in the fact that they are introducing windows and then shifting those windows, because in convolution also that is exactly what happens. The convolution filter shifts in 2 dimensions. So here maybe what they are saying is, let me just clarify this with GPT. I am not sure whether, because they don't have convolution as such. Let me ask. There is no convolution in Swin, but they have shifted windows. Is that what they are referring to when they talk about inductive bias? Is there inductive bias coming into picture in Swin? I just want to know whether they are saying that inductive bias in Swin transformer is coming because of the windows, the shifting windows. Does introduce inductive bias even though it is a transformer, not CNN. So what do they mean by inductive bias? CNNs have locality, translation invariance. This we know. Original vision transformer and data efficient image transformer removed all of this because they flatten image to patches. Attention is global, fully content dependent. Position embeddings are absolute, which destroy translation invariance. Oh, I see. Okay. Position embedding is also, relative position embedding is also one way in which we are bringing inductive bias. All right, that is very good to know. This works fine for classification where only the global summary matters, but for dense prediction like segmentation and detection, spatial alignment matters. Small translations should not drastically change the representation. So does Swin have inductive bias? Yes, a lot of it. Even though Swin has no convolution, it introduces CNN-like inductive bias through several architectural choices. Window-based local attention introduces locality bias. Shifted windows introduce some level of translation invariance. Hierarchical architecture, multi-scale bias. All right. Relative position embedding. Relative position bias is translation-friendly position encoding. Okay, I see. This is very, very good to know, because we might think that because CNNs do not have any, because Swin transformers do not have any, convolution operation, we might think there is no inductive bias, but that's not the case. In vision transformer, there was no inductive bias because the position embedding term was a learnable parameter, and no 2D information was being fed, except for the fact that there was 2-dimensional patching done. Other than that, there was no 2-dimensional information. But here, the shifting of the window itself is 2-dimensional. Relative position embedding is delta x and delta y. They are 2-dimensional. And there is hierarchical features because there are more number of tokens in the initial layer with less channel embedding dimension. As you go from stage 1 to stage 2 to 3 to 4, the XY dimension, the number of tokens reduce and the channel dimension increase. So there are all these 3 factors bringing different inductive biases, which are originally there in convolutions, but it was not there in vision transformer and data efficient image transformer. Then different self-attention methods. The real speed of different self-attention computation methods and implementation are compared in table 5. Our cyclic implementation is more hardware efficient compared to naive padding. Naive padding is you keep higher number of, instead of 2x2 windows, if you go to 3x3 windows after shifting, don't do cyclic implementation, add padding. But padding increases the number of windows that you have to process, particularly for deeper stages. Overall, it brings 13%, 18%, and 18% speed up. The self-attention modules built on the proposed shifted window approach are so and so. Overall, Swin transformer built on shifted windows are 4 times or 1.5 times this is times faster. compared to Performer, which is one of the fastest transformer architectures. The proposed shifted window-based self-attention computation and the overall Swin Transformer architectures are slightly faster. That's it. That's most of it. One important thing, if you stop reading the paper at this point, if you go away, one important thing which you will miss is, that in classification, Vision Transformer uses CLS token, class token. Here, how does it do classification? Here, how does Swin Transformer do classification? Nowhere it is mentioned. I wish the paper had some figure which explains what the architecture look like, because the architecture is obviously not ending with this. Where is the figure 3? Architecture is not complete here. Something has to happen to the token after this stage, right? For classification, something has to happen to the context vector once it comes out of here. Where is that? I wish the paper had one image instead of, being very frugal about the number of words and the figures. I wish they had done that, but they don't have it. But the problem is, if you stop reading the paper at this stage, you will miss out all those conclusions, which is why we should also read at least some parts of the appendix. So let's first go through the conclusion and then we'll come to appendix. We are almost done because this is a 14-page paper. Last 4 pages are anyway references. We are at the 8th page. There are only 2 pages worth of references. So if you have reached till this point, you're already almost done. So let's read through conclusion and quickly look at the appendix. Conclusion. This paper presents Swin Transformer, a new vision transformer which produces a hierarchical feature representation and has linear computational complexity with respect to image input size. Swin Transformer achieves state-of-the-art on COCO and ADE20K, significantly surpassing previous methods. We hope that Swin Transformer's strong performance on various vision problems will encourage unified modeling of vision and language signals. As a key element of Swin Transformer, the shifted window-based self-attention is shown to be effective and efficient on vision problems, and we look forward to investigating its use in NLP as well. All right, so that is the paper. Now, a few important details. We are pretty much done. In the next 2 pages, there is not much details. You can also skip a few things if you need. But one detail which I don't want to skip is over here. This one, image classification on ImageNet 21K. The image classification is performed by applying a global average pooling layer on the output feature map. So whatever comes out of stage 4, that is passed through global average pooling. And then a linear classifier. Linear classifier means after global average pooling, maybe you have 1 by some, let's say, n number of channels. And those n number of channels are now linearly projected into a C number of nodes. C is the number of classes. So if it's a 10 class classification, final number of nodes will be 10. So layer on the output feature map of last stage followed by linear classifier. We find this strategy to be as accurate as using an additional class token. So they don't use class token. That's the main takeaway from here. The Swin Transformer does not use classification token, unlike Vision Transformer or data efficient image transformer. And now let's read this part. The detailed architecture specifications are shown in table 7, where input image is this. Concat n by n indicates concatenation of n by n neighborhood features in a patch. In the main paper, we saw this n by n was 2 by 2. This operation results in downsampling of feature map by a rate of n. And 96D denotes the linear layer with an output dimension of 96. Win size as 7 by 7 indicates multi-head self-attention module with window size of 7 by 7. I think we know this. Regular ImageNet 1K training, we adopt 224 by 224. For other resolutions such as 384, we use fine-tuned models trained at 224 resolution instead of training from scratch. These are just some details about their implementation. These are some experimental details. Unless we are actually implementing this in practice, I don't think we need to spend too much time on this. ImageNet 22K pre-training. We also pre-train on 22K dataset, which has 14.2 million images and 22K classes. Training is done in 2 stages. For first stage with 224 by 224 input, we employ Adam. This is all fine. Object detection on COCO. For system level design. Yeah, I think this is all fine. These are all finer details which I will be interested in if I'm implementing this in practice, not unless that. So they are basically giving us details about their implementation for 3 cases, 1 for classification, 1 for detection, and 1 for segmentation. So this is the third part of segmentation. That's pretty much it. I don't think there is any major, logical or major architectural thing which you will miss from the appendix. It's all finer details. I think we can wind up the paper at this point. So that's basically the Swin Transformer paper. Although usually I don't like to skip appendix, here I have noticed that except for this section, most of it is details of experimental implementation. So I don't mind skipping at the moment. But we don't ideally want to skip a lot of things from the paper. We just want to read the whole thing. But the thing is, just reading about these experimental details are not fun unless you are actually implementing it, right? But if there were any logical things or some results, it would have been a bit more interesting to read the appendix. But that's not the case here. But with that, we can conclude the paper. I'm sure that you are feeling pretty, tired or at the same time satisfied if you have gone through the full lecture by this point. And we'll meet again in another lecture so soon. I'm not sure which paper I'll be reviewing for the next one, but it'll be something which is a natural progression based on what we have done so far. I would really like to review Visual BERT and Will BERT paper at some point, because they are also a good combination of, transformer and BERT architecture for vision language model. So let's see where we are going to go next. I surely also want to look at the data at the detection transformer paper also sometime in the near future. So that's it. That's the end of Swin Transformer paper review. We have gone through most of the paper and understood most of the things. Of course, the more we read, the more we understand. I had to take a break in the middle, so I found it really difficult to go through the whole paper in one sitting. I mean, there is nobody's forcing us to do it in one sitting, right? We just need to go through the paper slowly and steadily. That's what we did in this particular lecture. I would again like to reiterate that I wish this paper had more figures and better figures to make it easy for a normal computer vision or LLM enthusiast to understand. But unfortunately, that's not the case with this paper. It's only my personal opinion, but it's my strong personal opinion. I don't think the paper is that well written for someone to understand. It's well written for somebody who is already an expert in the field and who is already doing extensive experiments in this. So if that is the audience, yes, of course the paper is very well written. But otherwise, I don't think the figures and the writing is not very it's not very, I would say, beginner friendly or anything like that. So I think it could have been made much simpler if they had more figures in the appendix and more explanation somewhere in the paper. I'm not saying you need it in the main paper, either in the appendix or somewhere. If some figures were added and some figures to explain things like, how exactly do we do cyclic shifting. They have a figure, but I think it's too dense and it's too condensed. I wish the paper had a bit more elaborate figures. But anyways, each paper has its own thing, right? And sometimes, I mean, we should also give credit to authors. It's like they have already done an extensive set of experiments and they have already done an amazing work. So it's very easy for people to read the paper and pass critical remarks. Because running the experiments is already the hardest thing. Coming up with these architectures already is the hardest thing to do ever. So it also wouldn't be fair to the authors for us to be too critical about the paper. But I just wish, as a reader, it was a bit more beginner friendly. That's all, which is, I guess, a fair thing to say. Anyways, we'll meet again in another lecture with another paper. Thank you so much. See you soon. Bye.